This presentation is an overview of work I have been doing in the last few years with quite a lot of people who are all mentioned here. So the last one on the list. So it's trying to put in a perspective these different works which are touching on different aspects of the topic. So I will first tell you about what adaptive systems are and what this focus is, and then I will give some background on the useful notions I'm taking in the related work and literature, and then I will give some different aspects concerning language aspects and different feedback computing systems. So adaptive systems are more and more present in the sense that more and more systems, computing systems, have to reconfigure, change, adapt to changing environment conditions or to changing functionalities while running, so at runtime. And this is changing from a more classical view of computing systems where you deploy some big computation and you let it run and you get the results at the end. On the other side, you have another requirement which is sometimes contradictory, which is that you still want your systems to be dependable in the sense that they are actually fulfilling their goal, and in some cases where it's systems which are interacting with your personal life and belongings, you also want them to be safe. So these two things are potentially contradictory because this adaptivity is or adaptability is multiplying the working conditions of your system, and so you have a more complex job in order to assess this dependability. So that notion of adaptation, it is something which is quite classical in different kinds of control systems, robotics and so on, but it is relatively new in computing systems. I mean, really in the insides of the computing system. And it consists in having to react to changes in the operational environment. So this is more usual. It's like when your system is interacting with the outside world. When it is an open system, you have to react to what happens there. It can be changes in the implementation platform. Typically, you can have resources evolving, disappearing or appearing, or it can be related to faults. And you're going to have also changes in application objectives. You can have phases in applications which are corresponding to different application-specific objectives, and you have to manage your system in different ways according to these phases. So you want to automate that because classically this was already being done in big computing systems by the administrators, the system engineers. You would ask them to do something and they would do it manually when they have time for that, or they would observe how the large computing installation is going and have screens monitoring a lot of information and taking decisions and manually implementing actions in a control line mode, I would say. But this cannot last for a variety of reasons. One is that you can have systems which are too large, or if they are not too large, they are too complex, too intricate for a human brain to take appropriate decisions and manage these systems in a correct or optimal way. And another motivation for automation is that you sometimes want to have these systems adapting fast enough to changes, and you don't want to have a human person monitoring and taking the decisions manually. So one approach to answer to this adaptive computing problematics is autonomic computing, which I will introduce a bit further. But it's expliciting that notion of self-managed systems and the automated administration in the form of a feedback loop. The idea here is that if you want to automate this adaptivity, you have to perceives the notions, well, the events and the conditions under which you want to adapt. You have to decide on what you want to adapt, and then you have to implement that adaptation. So this is a feedback loop, or it is completely in line with what was presented yesterday at the other invited talk on smart environments. So here, it's really the same idea. You have to sense, to analyze, and to take decisions and implement them. So once you have that notion of control loop, and this is where I got interested historically in autonomic computing, what I thought is how people in distributed computing systems have in some way rediscovered the notion of a feedback loop, which is good news in the sense that once this need for a feedback loop is really explicited in that domain of distributed computing, then the relationship with the other domain where feedback loops are completely natural, this relationship can be facilitated. And that other domain is control theory. And this corresponds to the other requirement which I was mentioning, dependability. So dependability essentially means that once you automate the behavior of some system, you want to have some assurances and some guarantees on what it will be doing, because once you start it, it is running by itself, so you don't want it to go to configurations where it would be damaging systems in its finality, or even worse with respect to safety of goods and persons. So not all autonomic computing systems are safety critical in the usual sense of embedded systems, aircraft, trains and so on, but still, even without being safety critical, you still want to know how your system behaves when you automate it. So you need for design techniques and tools in order to design these feedback loops so that you know that they will behave according to what you want. And what can happen, what can go wrong, the kind of problems you have when you automate such a decision loop is that you can have, I'm just mentioning a few of them, you can have oscillations, you can have actions where you add some resource, remove some resource because you are oscillating around some point, and it's a bit useless to oscillate in that way. You would prefer the control to be at the right position and to be more stable. It can diverge completely and go to absurd decisions or values for the decisions you take, or it can be reacting too slowly. So quite a few things can go wrong, and these are exactly the... Oh yes, and another point is that you can also have automated administration where you are managing several different objectives at the same time concerning different aspects of your system, and you can have interferences between these different decisions. So all of these risks mean that you really need to have design theories and techniques in order to help you design correct automated systems, and control theory is exactly about that. It's only that it has never, until very recently, considered computing systems as a possible object of automation. Control theory is usually done and taught in electrical engineering departments, so not the same as computer science, and usually you just don't know them because it's not quite the same world. And they are considering electromechanical systems, chemical systems, a lot of things which we don't really consider when we are doing computer science. So in that sense, it's a new combination of control theory and computer science, which I'm exploring here. I would say that there already are classical interactions between the two. We actually know each other. One of them was classically computer science for control systems. All real-time systems, embedded systems, are mainly about implementing with computers control laws which are designed by control people. So this is the domain of embedded systems. Another interaction between the two is at a more theoretical level between models of continuous dynamics, say differential equations, and on the other side you have discrete dynamics, which are more using transition systems, and at the meeting of these two, you have hybrid systems where you have typically, well, you have timed automata and then a hybrid automata where you have the linear case, non-linear case, and so on. But this is at the mathematical modeling level. And so what I'm considering here is control theory for computing systems where you are designing these automation of the administration of computing systems as a control problem. And what I will particularly do here is to use one of the branches of control, which is more specialized in discrete event systems. And so I will not be considering here continuous control. So let me just introduce some of the basics of what it's all about. So autonomic computing, it's a fashionable buzzword in computer science. You have that every, half a dozen years. You have a new notion coming up, and but it's a nice one in the sense that what I like about it is this idea with it, which is actually quite well, not completely new, but quite new. The idea of trying to systematize the automation of the administration of computing systems. So it was launched by people at IBM like a dozen years ago, so not very long ago. And it's about designing network computing systems able to manage themselves through decisions made automatically without direct human intervention, or with minimum direct human intervention. So it's a quote here. The notion of autonomic computing is it's conceptual. It's not something formally defined, but still these concepts are a little bit worked out, and the kind of objectives which are targeted are self-configuration of distributed systems. When you are deploying a system, the fact that it would do so in an automated way. Self-healing is about going around or repairing faults and mishaps in a system. Self-optimization would be everything concerning the usage of resources, dimensioning computing power, memory size, or bandwidth, and things like that. And self-protection is everything we could concern security, typically. Against malevolent attacks, or also the others mentioned. So these subclasses of requirements each can be approached in different ways, but usually in a complete systems you can have several of them. And so one additional problem, additional to the fact of solving each of them, is to take care of their possible interactions, because you can have several of them, and then you need to coordinate their possible interferences. And so these are the objectives, and the basic runtime scheme of these autonomic computing systems is what is called the make-K loop. So the idea is that I have a pointer here.
It doesn't work on it.
No, I have this. Hardware pointer. But well, anyway, so you have this managed element here, which is your favorite computing system. So the idea is that you do have to have it instrumented in such a way that you can monitor it. So you have to have sensors. This monitoring can involve some processing of the information you are able to sense, because you sometimes have to transform it into analyzable data, and then you analyze it, meaning taking decisions on what you should be concluding from these observations. And for this you always can use some knowledge about the managed element, and from this analysis you get some decision which you then have to transform into a plan of actions which sequentially do what is to be done to reconfigure, and then you have an execution module here, which is transforming that into actual calls to the concrete actuators, which are the reconfiguration API, programming interface of your system. So this make-K loop has been proposed by the people who invented that notion of autonomic computing, and this is where I thought when I saw this is a feedback loop, but expressed differently, expressed in I would say, model agnostic way. So you can imagine, and people do, quite a lot of different things here. They do machine learning, AI planning, they do manual programming of very simple rules, or anything can happen here. And so my proposal is to say, well, there is it's my proposal, but not only mine, there is a small community of people in the last half dozen years, who is very active in saying this can be addressed by trying to use techniques and models from the control theory community, and that's one of the possible approaches, but there are others, of course. Oh, and I just wanted to mention that, so this domain is like a dozen years old, and it has two main conferences. One of them is called ICAC, and it will be held in Grenoble in next July. The deadline is over already, but you can still attend even if you don't have it. So I'm making a little bit of advertisement because I'm in the organizing committee there. Okay, so just a little bit about control for feedback computing. So the idea here is that, as I said already, when you have this feedback loop, you have an automated behavior which, when you launch it, can go wrong in diverse ways. So the idea is that you have to design it correctly. And so there are these basic notions from all control systems, which are that you have to define explicitly what you can sense and what you can act on. You have to define your objectives as well. And the thing is that sometimes you have an objective on some measure which is not the ones you can actually sense, or which is also not directly the thing you can act on. And so there is an indirect relation between what you can actually measure by the sensor and the metrics you need to take your decisions and the actions you can take. So this is where that modeling aspect comes into the picture, because you have to say how you transform the sensor information into the useful data on which you can take the decision. And sometimes you take a decision in terms of one metric, and then you have to transform that into actual orders you give to the actions you have. And so control theory is about that for a long time, as I said. And so, as I already said, it's not so usual in computer science to consider things like that. People are more used to design solutions in their heads, program them, and then either test them at runtime or do testing or do verification of the solution. And this here is a bit different in methodology. So the advantages here will be, this is what we claim, that you will have a better mastering of detection of uncertainties and obtaining stability and robustness of the behavior of your control system. But the difficulties are in building up these models, because the kind of modeling practices which are usual in control theory concern physical systems which do not have the same kind of inertia or continuous behavior and so on than computing systems which are more discrete in nature. So it's a puzzle for control people to model computing systems, because they are not used to that kind of dynamics. And you also have to build up these relationships between actual concrete system level sensors and actuators you have and the models you will be using. For example, I would just like to mention work by colleagues of mine who wanted to do some admission control in web servers. You have a flow of requests coming in, so it's very discrete in some sense, and you have to take decisions on how much they can cost and if you accept it or not, and you have to reject these requests if you have too many of them, in order to avoid, because otherwise your system would crash. And so the problem is so you have these request messages and things, but they ended up by choosing to use a liquid model, and they modeled the thing like a tank with liquid coming in and coming out, and this was the appropriate model for the kind of objective which they wanted, and it was a continuous abstraction of a very discrete model, which is not very usual, but which is interesting because it means that the model you use in control does not need to be an exact physical detailed representation of what you have underneath. There is some know-how in control in order to have the... They used to say that all models are wrong, but some of them are useful. That's what they say in control theory. And it's an interesting rule of thumb. So what we will try to do here is to do that kind of stuff. So the way you model a system, it's a research topic in the sense that modeling computing systems in such a way so as to control them is not usual. So this is what I will do, but I will not, as I said, I will not be considering continuous model of discrete differential equations and so on. I will be considering what's called discrete event systems in control, and they are, it's a small community in the big control theory community, and the kind of models they use are Petri nets or finite state machines, just like we do after all. But they use it a bit differently. So I will be using automata-based models related to synchronous programming and a special variant of discrete control which is compatible with that. So these automata-based models, in computer science we usually call that reactive systems, and we have programming languages which are called reactive languages and which are used just for that. So a well-known one is state charts. You might all have heard about state charts, and maybe some of you work with it. I'm not using that one because the other one I'm using here, I have an inclination for it, but it's all of the same family. The idea is that you have languages which enable you to program systems where you are reacting to a flow of inputs by outputting a flow of values. And you have some internal state. You have data flow languages, equational languages for doing that kind of stuff, and you also have more automata-based languages which look like this one. So this is an example. So it is a data flow node actually. It is called delayable, and it has inputs here, 3 inputs, R, C, and E. So flows of Boolean values. And it will be outputting 2 flows of Boolean values, A and S. So I could have put little arrows here, but you have flows coming in and flows coming out. And what it does is that it is initially here in some idle state. And when R is true, R is a request, then according to the value of C, if C is true, I go to the active state. And so this small automaton is actually modeling the control states of some computation task. So if it is requested and the control says OK, then it goes to the active state, and when E becomes true, it means that it's the end notification, it comes back to the idle state. If C is not true, so here we have installed some controllability in the sense that we have an input which tells us if we have the right to do it or not. Then I go to the wait state and I wait until C becomes true to go to the active state. And on the transitions going to the active state, I have this S here after the slash, which means in the state charts like syntax, it means S is true, and so I set the actual starting signal to the system only when I'm really activating it, and so it's only indirectly related to the request here. So this is a small control scheme which corresponds to the activities, the control states of computing tasks which can be delayed, hence the name delayable. So this small automaton is not very complicated to design. The real syntax of the language I will be using is here, but so it's textual, but it's quite close to this anyway, because you are defining an automaton. States, the transitions are going out of the states, and you stay in the state until some condition is true, then you go to the next one. And when you are inside the state, you give values to the output flows. And so these equations here are different according to the state, which is what we call mode automata in synchronous programming, which means that we are having different data flow behaviors inside the node, between which we switch following this automata. Okay, and so I'm using synchronous languages, so it's a kind of languages which is at least 25 years old now, which has been used in industry and so on. And the word synchronous here means that you can compose such automata in parallel, and then what happens is that a bit like in sequential circuits, all nodes, subnodes which can do a step do, and they can exchange some values within this global step, hence the name synchronous. And you can also have hierarchical composition of automata as well, just like in state charts. So this kind of automata-based programming languages are nice because they have compilers, they have code generators, and they are based on a model which is finite state machines upon which you can do verification, and so it all boils down to having a state vector, a state variables, and a transition function, which is transforming current state value and input value into a new state by the transition function. And you can do model checking of that. So most of you must have heard about model checking. It's about exploring the reachable state space of such a system in order to know whether or not some state is reachable. What I'm using here is a more control-related version of that kind of state space exploration, where you first declare a partitioning of your variables between the one which are declared uncontrollable and some other ones which are declared controllable. And then discrete controller synthesis for a given property, it consists in exploring this state space in such a way that it is computing what are the values of the controllable one, the controllable variable, such that the control system with this restricted behaviors is satisfying the property of interest here. So we are using mostly invariance, meaning remaining in a subset of the state space where some property is true, and control then will give values to these controllable variables in order to inhibit all the transitions which could possibly lead you out of the good states space. And it is not trivial because what can happen is that when you look at one step ahead, you can say, oh, the next state is okay, and the next one too, but you can have sequences of uncontrollable transitions which lead you out of the good state space, so you have to go back and backtrack up to the last choice point where you can avoid wrong behavior. This is why it's a model checking related algorithm of exploring the state space. Okay, and so this technique, which is called discrete controller synthesis, it is much less developed and explored than model checking because on the one side, it's studied by people in control theory who are not computer scientists, so they do not develop tools and things. And on the other side, people in computer science have developed enormous work on model checking, but they are not so much interested in this synthesis approach. Even if there exist some people doing it, it's much less developed. But still, the reason I use synchronous languages here is also that there exists a tool done by my colleague Hervé Marchand in Rennes, who is one of the co-authors here. And so there is tool support available for this technique. So now I'm going to briefly present what we did at the programming language level. So we said...
so can you say something more about uncontrollable? Do you
about?
mean about the term uncontrollable? The variables there.
Uncontrollable, well, yes, typically you are developing here a controller for a system which is underneath. And so the information you sense, the events you receive, you don't want to ignore them. You don't want to inhibit them. You say, I am not controlling them, I am accepting them. And so the idea here is that what is controllable is the things upon which you can have an influence, where you can make a choice, and the uncontrollables, you cannot. And so the idea is to have a controller here, which is choosing values of the controllable variables whatever the possible sequences of uncontrollable variables. So your sensor input is here, you do not control it, and from this sensor input and the current state, you are going to decide what are the values of my choice points, of my control points, which I have to choose in order for the system to have the correct behavior.
Okay, so you don't mean controlled and uncontrolled. You mean controllable and uncontrollable.
Yes, controllable and uncontrollable. Yes. That's what I mean. Yes, and what I write here. Yes. So BZR is a language we have defined on top of the previous language I was showing to you with these automata. And the idea is that considering a reactive node, which has a semantics which is essentially a finite state machine, you add what we call a contract, so it's a special interpretation of the word contract, and we declared which are the controllable variables, which will be local variables to the node, and we have an enforce statement which is followed by a simple Boolean expression, and by compilation we will have a compilation which is calling the discrete controller synthesis for a controller enforcing invariance of the subset of states where this predicate is true by using the declared controllable variables. So in that sense, it's putting discrete controller synthesis, which otherwise, if you read the literature, is a very formal notion with much technicality, but this is encapsulating it in a programming language, which is then half imperative, half declarative, in the sense that you imperatively describe possible behaviors, automata as I showed before. You can put them in parallel to build big automata from small ones. And there is a declarative part here where you say, oh, and out of all the possible behaviors of this complicated automaton, I want to keep only those which are satisfying this property. So this is a small diagram which shows that here you have the automaton model, and internally you will have a synthesized controller restraining this automaton in order to keep only the appropriate behaviors. And sometimes it does not work, because like in any control problem, if you don't have enough observability on your system, if you don't have enough controllability, or if you have a too strong objective which you give to it, it can happen that there does not exist a controller to do that. Or it could also happen, because I'm essentially explaining it in the Boolean world, but if you have two complex expressions here, it can be that the algorithm do not find the solution because they are conservative, of course. But still, so it does work. So in the paper you have references to papers where we fully define the operational and denotational semantics of that language and explain how it is compiled and so on. Okay, so what we claim here is that the advantage of this approach is to compare to the, I would say, the state of the art of programming autonomic computing systems is that most of them are programmed manually using Java and C. So this is, for one thing, a higher level language in order to describe the behaviors you want. The other thing is that when you get a controller, it is correct with respect to what you defined as an objective, because of the algorithms which are doing their job properly. One interesting property here, which I didn't mention, and which is also a reason why these discrete controller synthesis techniques are not simple, is that they try to find the minimally constraining relation on this controllable variable to keep the maximum possible behavior. And so you have a notion of maximal permissiveness here, which I think would be hard to get if you, in simple cases, you can program the solution manually and verify whether it is good or not. But thinking about all the cases is hard for a human brain, harder than for an algorithm. And finding the least, the most flexible controller, which is not inhibiting behaviors which actually do not cause problems, this makes it even harder when you do it with the brain, and this is what algorithms are good for. So these are the advantages of this technique. And the last one is that in such a context of a programming language, you really have executable code at the end, which is essential when you want to speak with people in operating systems or hardware architectures, because that's what they want. They want to have some executable code at the end. So here we have it. But there is a problem, which is of scalability. Just like for model checking, the algorithms are essentially exponential, so it's costly, of course. And so it means that you have to take care of that. So one answer to this is that just like in model checking, efficiency of algorithms is progressing, even if you still have this wall of exponentiality. But the other answer which we are proposing here is to have some modularity in order to cut up a problem into sub-problems and have less complexity. So we have this notion of contract in that language. I skipped the assume part in the explanation, but well, we have an assume part which says that when you want to enforce a goal, as I said, you can also have a part here where you can make an assumption on some relation which holds on the values of the input. And you can also have automata here, which means that you can also make assumptions on the sequences of values which can come in. But so a node can have subnodes, which have local contracts, and then when you compile the contract of this node, so you do discrete controller synthesis, not expanding the sub-automata of the subnodes, but considering this contract, and this is why we call it contract, to be a usable abstraction of what goes on underneath. And then what you do is that at that level you solve a problem where the control objective, invariance objective, is not only G, but the fact that the sub assumptions are satisfied. And reciprocally, what you can assume here is that given that the sub-assumptions are satisfied, the sub-goals are too, and then you can use that as an assumption here. And so this language exists, it can be used. There is a web page here, and you can ask us for a copy. We are freely distributing it. And so it provides a nice basis for the design of controllers. And I will now, in the remaining time, show how we use that for different feedback computing systems. I like the word feedback computing because it talks about computing, and it says that it has some feedback effect, and so it's a nice buzzword actually. And there is a workshop called feedback computing, which I co-organized some years ago, and which is where it's the only workshop which is specialized on this topic I'm telling you about, of control for computing. So it's a nice one. Okay, and so to make the relationship between what I just showed and autonomic computing, I would say, so there is this make-k loop, which a lot of people in software engineering are using, and even people in these concrete operating systems, they understand that and they accept this make-k loop. So this is an informal translation between the make-k loop and the transition systems I'm using. And so I say, okay, the inputs and outputs are the flows. This is quite easy. The current state of the automaton, global automaton, would be that knowledge here. And we have objectives or a controller after the compilation, which is taking into account these inputs of the current state and providing appropriate values for the controllable aspect in your system. And then you have to transform that into actual actions, which are going to the input. And so the controllables are here, as well as the input and state, and it all goes there. So the typical things we are going to model, and I'm going to show examples of that, are resources in a computing system, which can be on, off, or which can be occupied or free. They can also have different levels of functioning, which are costing more or less resource and things like that. We will have tasks, including that delayable task which I showed you, which is one of the simplest examples. where you consider activities, starts and events, of course, changing modes. A task can continue running, but change mode with different resource usage and so on. You could also have checkpoints. I have some work about things like that, in the sense that you can have an automaton keeping in its memory, in its current state, at which checkpoint you are, so it tells you if you have to start again, then you start from that point in the automaton. And you have, so this is really computing results, the tasks which you have, and applications also give interesting information in the sense that if you have an application which is going sequentially through phases, like in web service orchestration and so on, if you know in which phase you are, this is important knowledge to have here to take your decisions appropriately. Okay, and so a last word to say that this basic loop, it's a conceptual notion which can be explicited at very diverse levels. It can be at low level, having to run fast and on detailed information, or it can be at much higher levels. I mean, differently to classical embedded systems, real-time systems, where you consider things which have to run fast and you have small deadlines, and so you have to squeeze your program into small resources to react fast enough. This autonomic computing thing is also applied in like data center, where sometimes the feedback loop has a period of several hours or even days. But it's still a loop, and if you automate it, so if it's once every several days, you could say a human can detect that it is going wrong and diverging. Maybe, but still, you need to have some design for those loops. What I mean here is that some of the loops can be slow and can be at very high level, and in that case, they should not have a complete detailed model of what's going on below. They should have the appropriate model to take their decision at that level. So a first application I'm going to explain here is concerning reconfiguration control in FPGA-based architecture. So FPGAs, it means field programmable gate array, and it's a special, I don't know if many of you know about that, but it's a kind of special hardware. Essentially, it's a very large array of small electronic components which are like a logical gate, of which you can program what operation it should do. You have inputs, outputs, and you have additional inputs telling you if it's going to be an AND, an OR, a NOT, or something like that. And so you have extremely large arrays of that, which means that you have hardware which is not as efficient as application-specific integrated circuit, but where you can download what they call a bit stream, which will be transforming this gate array into a specialized processor for some computation and so on. And so it will be, as I said, less optimal, less efficient than what an application-specific integrated circuit, an ASIC, would be, but it's potentially much more efficient than running a software algorithm on a general-purpose processor. Okay, so that's one thing. So it's like a programmable hardware. And the other thing is DPR. It means dynamically partially reconfigurable. And so these things, FPGAs, so they have a large array which is reconfigurable, and this can happen dynamically. At runtime, you change the logical function which is implemented by that system, which means that at runtime, you can also do it partially. You can change part of the array and its functionality. It means that at runtime you can change the hardware which is running your application. So it's an interesting thing. So there are people in the architecture community working on that, and as usual, they're working on the platforms, instrumenting them, making it possible to dynamically partially reconfigure, and they need models and decision techniques to close the loop to make it a loop. So this is one proposal where we will be 10 minutes. So where we will be applying this method I was showing you and model essentially in terms of finite state machines, automata nodes, the possible behaviors of the different elements of this system. So you will have the architecture, and we will have each of the tiles, as they call it, each of the parts of the reconfigurable area modeled with a behavior. We added in a little battery state here in order to play with it. We will have tasks, which can be delayable or not, and the tasks can have different modes. So what they have, for example, for an image processing task, which they implement on that kind of hardware, they can have several versions, doing pattern analysis with different quality levels, and these different implementations take more or less surface of this big array of gates, and they are more or less fast, and they are doing their functionality with different levels of quality and different consumption of resources, which is interesting for us, so we will be modeling that. And there is an application graph, which is usually a dependency graph invoking tasks one after the other, and so on. And so what we will have here in the knowledge, in the state, will be the progress in the application program, task graph. So it means that at each compilation, what we are doing is that we are kind of generating an application-specific manager for these computing systems. Huh? So, which is also a bit special compared to other approaches where people try to have an operating system which, whatever the application running on it, is managing resources well. We take the application in the picture and we generate executable code for each particular application, exploiting the knowledge we have about the application. So we will have a state about the activity of tasks and the state of the different hardware pieces. And the choice points we will have, the controllables, will be the choice of modes. When we are starting a new task, we will have to choose which one of its implementations we take. We can have some delay control, as I showed previously. We can switch on and off the different reconfigurable parts of the large FPGA, because then you save energy, and that's it. So we will be modeling the possible behaviors of all these things. Yeah. And separately, we have policies here, or strategies. So you have to say what are your objectives. And here we will have quite intuitive things like the exclusivity of resources, of tiles in the FPGA, bounds of the power consumption, instantaneous power consumption, like power peaks, and the reachability of the end state of the task graph, which is desirable, and some optimization. So as I said, we have models which are individually essentially quite simple. Like for each of the reconfigurable parts, we have an automaton here, two states which says whether it is in active mode or sleeping mode. And in sleeping mode, it will be implemented with a clock gating mechanism, which is cutting the clock for that part of the hardware, and then it still consumes a bit, but much less than when it's clocked. We will have task models with either state, wait states, and different active states according to the mode. And the application task graph is modeled essentially by an automaton showing what is its progress. So translating from a dependency graph to an automaton like that is easy. And then the interesting thing here is that when you are, so this is an extremely simple graph giving a small automaton. When you have a task graph with parallel branches, and if you have some exclusivity constraint between one task here and another task there, so this part of the model tells you if, when you start one of the two exclusive tasks, if the other one has already been ended, in which case you can choose the implementation you want, or if it's busy executing, or if it is still to be done, because that automaton particularly gives you knowledge about the possible futures of your system. Okay, and so this slide shows how the things end up executing somewhere because you have to execute that. So as I said in the beginning, these synchronous languages generate executable code for the controlled automaton. And it's essentially a reset function to initialize things and a step function. And you have to call that step function. So according to the flow of observations, each time you have a decision to take, you call that step function, which will be doing it appropriately. And you interpret its outputs and transform them into concrete actions. Okay. So in the 2 minutes remaining, I will just mention another application we have been working on, which is interesting because here I can show you a bit that modularity can come into the picture. And that it can be concerned in different systems. So here we have a multi-tier application in a data center with replicated web servers and load balancers. And here the idea is that you have pre-existing in legacy managers done by people not with my favorite techniques, but which work, and they don't want to change them. They have self-sizing, which means that if the load of in these web servers is increasing, then you would add more servers, and if it is decreasing, you are shutting off servers in order to save energy. And so adding a server takes time and so on. So it's not completely trivial from an operating system's point of view. Self-repair is when you lose a server or a load balancer, then you have to start a new one again, reconnect things, etc. So it's again not too easy, and they don't want to change it, so because it was hard to design. And consolidation means that from time to time, what they want to do is to see what computations are active and if they can group them together on a smaller number of machines to make some saving. So again here, the problem will not be each of these managers, but the coordination of them. Because what can happen is that if you have the self-repair which is busy repairing a load balancer, for example, then you know that that load balancer is not working, so the web servers below are not receiving requests, so they are in underload, but you should not switch off the servers, because as soon as the load balancer is on again, they will receive a lot of requests, so you will have to switch them on again. So you have to coordinate these different pre-existing managers. So what the state here on the level of the model is the activity of the managers, not of the servers and things, but the managers. And we have several tiers of these kinds of systems, so we will have several levels of coordination. So in each tier where you have replicated web servers, you have to coordinate one repair and one sizing manager. You have several of these replicated tiers. Each of them has a load balancer, and the load balancer can be repaired itself, so you have to coordinate the repair with the previous thing. And when you have several tiers, you have to instantiate several instances of this previous thing into a hierarchical framework. And so this is to give you the idea that we worked on these modular aspects, and it gave the expected result of making it possible to synthesize controllers, which otherwise was explosive because of the exponential aspect. Which leads me to the conclusion. So this was a quick overview. The paper gives not so much more details, but a lot of references to papers with plenty of details. It was meant to show that the same method can be applied to a variety of different computing systems, because people from the FPGA community and the cloud servers community don't talk to each other much. But this is one point of interaction where the generality of it is that you want to design control loops with well-mastered behavior. So on the logical discrete aspects, this is one approach. Perspectives are diverse. I think there is a lot of modeling work, because modeling these systems is not intuitive, because it has not been done much. So it's not a theoretical problem, but it's a more modeling problem. Formalisms are there, but how to use them, how to decompose problems is something. On the more formal aspects, we have new, especially with my colleagues who are more in these formal aspects, they are designing new algorithms with logical numeric aspects which are very interesting, with some static analysis techniques and so on. And domain-specific languages, I think, would be nice, and I'm working on that, because even asking people to program in terms of automaton is not in the terms of the entities they want to control, so domain-specific languages are interesting. And adaptive control is making things even more dynamic. So this is it. Thank you.
Liveness, big progress towards certain goals.
So liveness in that sense, so liveness in the usual sense, no, because so there are two parts to my answer. One is that there are approaches in program synthesis in computer science where they do consider liveness, but here it's approached in a view which is more about control, and then typically we don't really know what that would mean. In this, we could have assumptions on liveness of the uncontrollable occurring events, which could help us design controllers, but we don't really know. But another notion of progress which we are interested in is related to that notion of attractivity he was asking about. You can favor choices which make you progress towards some state, which is not liveless. It is making choices which still depend on, it's not live in the sense that you, it still depends on your inputs. But well,
it's beyond safety. That's
yeah.
That was
well, no, it's encoded into safety, in the sense that when you have choices, you favor choices which are making transitions towards that state and avoiding possible loops in your state. So I mean, it's encoded into a safety control problem.
And last question. So, and how do you compute this control rate?
This is this is done by my colleagues. So essentially, my colleagues in Rennes. Essentially, you have it's a bit like model checking. You have a representation of the state space. You have that set you want to make invariant by control, and you have a pre-function, and you are computing a fixed point down to the one where it's okay. So I'm telling it briefly, but if you know model checking algorithms, it is quite similar. But
is it BDD based?
The present tool is BDD based, and it's like so. The present controller synthesis tool we are using has been developed 15 years ago. So it's like using 15-year-old BDD techniques. But as I said, not many people are developing controller synthesis tools, so I did experimental work with that one, but we have a new one which is using more advanced, I think it's ADDs, arithmetic DDs, and SAT techniques might be changing quite a lot of things.
Long back, that famous writer, Benjamin Franklin, wrote a quote. It says that three may keep a secret if two of them are dead. So, more and more people are connected with different channels. So, security issues, privacy issues would be much more challenging. And in this talk, I'll try to give you an insight of Internet of Things, then I'll bring security and privacy issues in the context of IoT scenarios and applications. So I shall be using some other material, third-party copyrighted material in this talk for the sake of educational purpose only. As a result, the usage of this presentation is restricted and is falling under usual copyright usage. So what is Internet of Things, or in short IoT? The definition, there are many versions of IoT provided by different research communities, but the definition of IoT evolves around the central concept, that is a worldwide network of interconnected objects, where objects must be addressable through unique identity, accessible through internet, sometimes through intelligent interface, and objects must be self-organized, self-repairable, and manageable. That is, IoT is a world of intelligent, adaptive, self-organized sensors, actuators, others embedded devices and systems that use various network technologies to connect each and every objects of physical world to the conventional web of world. So it is a worldwide network which will facilitate connecting each and every physical entities or objects to the conventional web of world, and that is that IoT paradigm. Now if we see that that pre-computer era, the postal system, so basically human to human, that system. Then with wired computing era, human to machine. Then again wireless computing is human to machine. Then now it is machine to machine. In that machine to machine, so what does it say basically? That is first machine, then two, using that communication technologies, then last machine. So in the first part of that machine, that device, for example, water valve, which is monitored by means of sensors, or air conditioning machine, which is monitored by some other devices or other computing that machine. Then that network which facilitates end-to-end connectivity between machines, and with the help of radio waves, access network, gateways, and backend server. Then last part of this machine, that for example valve, which is instructed to actuate, which is instructed to respond, or device like computer which automatically controls and instructs other machines. That means that transition from human to machine into machine to machine requires these three important features. The first one is that instrumented, that is event capturing and filtering for timely response, where embedded computing will play a central role. Then interconnected, anytime, anywhere, anything connectivity, so that is reachability feature. Then intelligent, which will involve human computer interface, user behavior, business intelligence. So that analyze, that provide interface, through that interface, that last part of the machine will respond in a real-time manner. So if we look at the scenario, that global machine-to-machine connection, so this was the research study by Machina Research. So here you can see that now we are 2050. So in global scenario, almost 5 billion that objects means are being connected. Now if we go to that 2020, then it will be more than, it is not 14 billion, Now it is predicted now at 20 billion at least. Then now if I look at that our continent scenario, that Asia machine to machine connection, so it is almost 50% of that connectivity. Then who are the basically driving forces in machine to machine connection? Now if you look at that, so there are six that forces, so intelligent building, then consumer electronics, utilities, automotive, smart cities and other machines, out of which that intelligent building and consumer electronics, so they are basically owing the maximum share of this present scenario. So consumer electronics and intelligent building. So we are now using that machine to machine, that computing. So that will be connected with web of world. Then that web of world, with the help of that internet, we may see in near future that the reality of Internet of Things. So this is a typical scenario of IoT, where you can see that home automation, then healthcare system, this is transport systems, so they are basically interrogating each other. Then again entertainment, utilities, office automation, home automation, then smart grids, again consumer electronics, remote monitoring, mobile technologies and other specialized domains, that military application. So based on that application goal, means one will be able to connect to other entity with the help of that communication technology, and where internet will be that communication backbone. Now IoT perspective, so basically you can consider 3-4 perspectives. So first one is the technological perspective. Now IoT requires context-based technological development, keeping consumers' convenience as the primary concern. So user friendliness, that interface, so that would be a primary concern. Then security, privacy, trust, ownership of data as well as services are important concerns that would bring significant changes and opportunities to manufacturers, developers, service providers and service consumers. Now the business perspective, then who are that maximum beneficiary? So tremendous potential of electronic business has already been arrived, and that is going to be scaled up in multiple folds with the help of IoT scenarios. The factors that could work for adopting IoT in industry are standards, specifications, compliance, interoperability, integration, security, privacy and ownership issues. And the maximum beneficiary of IoT infrastructure is industry itself. So they will basically provide service, and service consumers will basically return the revenue to the industry. Then economic perspective offers two kinds of incentive. One to consumer, another one is to supplier. Now consumer would benefit from IoT infrastructure in terms of time management, that is connecting home appliances to office premises. Then flexibility, so anytime, anywhere accessibility of that service. Then security, for example, door, vehicle, lock, unlock, alarm, which will be basically monitored with the handheld device. And revenue, that is smart energy, smart transport and smart shopping. Then suppliers part, suppliers would benefit by generating revenues in terms of smart services, smart devices and smart technology to assess vulnerabilities and addressing them for consumer satisfaction. And small scale service providers can use third party infrastructure for resource sharing, resource pooling, and large scale provider can make best use of small industries services. Then human perspective, intellectual property, technologies and information on core processes reside in human minds can be used in IoT in a controlled way depending upon consumers and supplier requirement. Manufacturers can act as a single source and a single point of failure for that mission critical application. And security and privacy of objects could pose a serious threat to application and human as well. Now, as of now, so few specifications and standards are there which can provide guideline to that IoT scenarios and applications. For example, IATA, that low power personal area network over IPv6, then routing over low power noisy network, then core and TLS, and in the context of that constant environment, it is now DTLS, that is TLS over user datagram. Then machine to machine standardization, and IoT has already, IEEE has already started that IEEE standard association, which will basically devise different specifications for that IoT applications and integration with different that integration with heterogeneous applications. Now, who are the basically that driving forces which will contribute to these IoT scenarios or applications? So primarily embedded devices. Now if we consider that smart office, that wireless sensor network and RFID system, similarly smart city, wireless sensor network, RFID system, smart agriculture, again wireless sensor network, then smart transportation, sensors, RFID, smart metering and smart retail. Again you can see that sensor network and RFID system. So they are going to play a central role in the IoT that scenarios and applications. Now if you consider this application, the smart shopping cart. So a shopping cart that has that display board, and assume that shopping center has all items which are RFID tag enabled. Then that card has one display, and that once you put the item inside the cart, then it is scanned with that reader, and you can see that okay, what are the items that you have put inside the cart and what is the total price. Then again you just swipe your credit card, you pay bill and move on. Now smart refrigerator, it can recognize what is being put in it. Again, all items, the assumption is that all items are tag enabled. Tag is basically a small chip which has limited resource. So all items are tag enabled. When you put item inside the refrigerator, or when you remove that, again that refrigerator, it has that it provides that reader capability. It scans that item details and it will show you what is been inside, and when you move out that item from the refrigerator, again it removes that part. Then it shows that recipes that most closely match with what is available in it. So without applying own mind, it will give you okay, you have these many items, so you can tonight you can have this recipe. Then that one can access the refrigerator from a handheld device, means from anywhere, from office or from shopping center. If you like to see okay what is there inside that refrigerator, you may not recall that whether milk pouch inside that or not, then you can simply talk to the refrigerator, you can get the information, and based on that you can decide. Then you have smart vehicle, smart transportation system, then we have seen that talks and other research discussion that says basically that smart energy, then autonomic computing, again that smart sensors. So you can have finally smart city, which will basically provide means inside of that Internet of Things scenarios or application, and when you have that Internet of Things in its desired shape, then you can say that it is smart planet. So basically the IoT actors are that sensors, RFID tags, or you can say that constant devices, which are the main actors in IoT scenarios and applications. Now this constant device is a low cost, low power device that might have following functionalities, which it can communicate on a short range like sensor and RFID. It can sense environmental data and perform some that inexpensive operation. And the communication between devices and other entities rely on radio wave, which is susceptible to many attacks or threats. Since communication, that sensors, then tags, so they will basically use wireless channel that invites several threats, which may pose means serious bottleneck to the application goal. Now that constraint, basically resource constraint is one constraint, and what is the implication? That protocol must be energy efficient. So it's that application should not cost much that computation and communication over. Then operation means that devices are being deployed in unattended environment. So operation unattended, that means adversary can capture any device. Now when adversary captures a device, then adversary can use that captured device for adversary's intended goal. Even though you put that self-healing or self-repairability feature, but that may not be sufficient unless you replace that captured node with a legitimate node. Then not tamper resistance, that means adversary can compromise device data. Lack of central control, that means it requires cooperative data exchange. So actual goal is end to end, but it requires several steps to reach that destination. So that cooperative data exchange would be a demand. Then no pre-configured topology, that is device doesn't know neighbors in advance. So in dynamic that pattern or mobile nature that devices, so you do not know, means a priori what would be that actual that network. So that network structure is basically changed time to time. Now if you look at this application, mobile that healthcare application, then it involves primarily these three domains: network domain, device domain, and application domain. And network domain means that application, the goal is that it will basically predict some characteristics of human body with the help of that either implanted embedded device or using that embedded device. Then, so using that wireless body sensor network, then these are basically the device domain. So you can consider that backbone router, video sensor or gateway. Then with that device domain, then it will give the data to conventional network that we are using, the traditional, that wired and wireless network. Then that application can provide all the required information, that is managing medical record database, patient portal, and here is the final that client's requirement. So client will get actual data through that interface, intelligent interface. And that application domain, so it requires data collection, then data transmission, and finally it should provide data access to the that service consumer. Now, since we have to use that constant devices in IoT scenarios, which will basically talk to that traditional computing device which follows, say for example, that OSI layer. That means that constant application data has to reach to the HTTP, that application layer protocol. Once it reaches to that, then we have solution from HTTP, that application layer, to the physical layer. We have plenty of solutions which will provide that security solution. But you need to translate, or you need to map that constant application data to that conventional application protocol, that is HTTP. So for that, constant application protocol is one of the that interesting protocol which one can use to solve that part, means translating or mapping that constant device data into that HTTP, that format. So here you have that constant device. It's not that smartphone, that means old phone you can consider, or that sensor or tag. Then it will use that, instead of that HTTP, it will use that COAP. In place of HTTP, you can use that COAP, then slash, then all other that format, that host means host ID, which URL, then port, application, and query. So instead of that HTTP, you need to use that COAP. Then that COAP protocol, and here you can use multiple proxies. Then that proxy will basically translate that COAP into HTTP. Once you have HTTP, then you have that entire solution. You can use that TLS and other security solution which will basically protect that application. Now COAP basically is an application layer protocol that enables web services for constant devices and networks. Now using that constant application protocol, so you have that smart home, that is home automation. So here use with door, then air conditioning machine, or you can consider refrigerator and toy, whatever you can. Means assume that each object inside the door has some computing device, and you can basically talk to any object with that constant application protocol. Then here is healthcare application. Here is suppose that smart energy. Then in between this, you need to basically map that constant device data to HTTP, and once you have that HTTP, then HTTP to transport layer and network layer, MAC layer, physical layer. So that solution one can find in different with different alternatives. So that constant environment, you have to basically transmit data to that traditional computing environment, and within that constant environment, again you are using that wireless channel or radio waves, and within that traditional environment one can use that wireless channel, wired channel. So that means when you use that public channel or wireless channel, then security and privacy issues are important concerns. Now, internet is possibly the victim of its success as far as security is concerned. So it gives many interesting solutions, but you can get that solution with some care. Means that security privacy issues must be addressed to get that internet solution. Now when we say that security and privacy, so one has to be sure means what does that security mean. Then you need to first figure out what do you mean that okay, I need security, or I need security for this constant device, or I need security for my application. Now in an objective sense, that security measures the absence of threats to get the solution. Again, you can borrow that famous quote, means three may keep a secret if two of them are dead. Means if the universe has only one human, then ultimate security, if two persons, if they talk to each other, then you have to basically achieve that security. So in an objective sense, security measures the absence of threat to acquired values, but in subjective sense, security measures the absence of fear that such values will be attacked, means such values will be blocked or will be tampered with, means you may not get the intended solution. That fear is there. Then you require that feature, no, I need security for my application. That is, security is a system property. Security is much more than a set of functions and mechanisms. It's not that crypto functions or crypto algorithms. So if you have good algorithms, if it is implemented badly, then application may not provide the intended security. Similarly, the privacy, again one has to think, means what is the application goal, means what you are looking for, that privacy part. Means one can say that object privacy, and in that case that you are dropping, tracking, stealing data would be the attacker's goal. An attacker will not provide these services to the legitimate customers. One may think of having that location privacy, context privacy. I mean, one can say that on one hand, entity who carries device enabled doesn't want to be tracked by the terminal, which could preserve its privacy. Means suppose my cert is tag enabled, or that wristwatch is tag enabled. Now if I put my cert inside a room, then I need to make sure that no one will be able to track me, means where is my cert. So that is basically object privacy. You need to ensure that privacy is not compromised. Then location privacy means, on the other hand, again application may need the feature. On the other hand, one requires tracking device enabled criminals or suspicious objects in a controlled way, which could save money, national assets and human lives. So another intention, another goal could be to track the item, means where is that item is going out, so that you can monitor the activity of that item and you can respond accordingly. So first one, it doesn't provide you to monitor that part, and the second part, it requires to monitor the object. So again, based on the application goal, one has to consider that privacy feature in the application. Now in the context of IoT scenarios and application, that when you say that security and privacy challenges, means that could involve this authentication, integrity, confidentiality based on application requirement. Now here authentication is not traditional that entity authentication. So here goal could be that universal authentication, means you authenticate at the sender side, then when it is reaching destination site in between sender and receiver, if there are several proxies, so those intermediate proxies may not require to authenticate that data. So you authenticate at one end, let other end accept that entity without authenticating that data or entity with the intermediate nodes. So that would be interesting security problem or research problem to explore it, that in the context of IoT scenarios and applications. So it is universal authentication, not at all open authentication. Then identity management, so trillions of objects are going to be connected by each other, and each object will have some unique identity. So again, the problem is how to manage this high volume of identities. Then authorized data access, and this one is much more challenging nowadays, that availability of data. So that authentication, integrity, confidentiality, means some sort of solution exists and people may find some intended solution for that security attribute. But availability of data when you use the public channel, that wireless channel, is a very demanding solution. Means, that is, availability of data would be a big challenge in near future, or would be a big challenge in the context of IoT scenarios and applications. Then lightweight security protocol for constrained environments, privacy preserving service, and finally trust and data service ownership issues. Now, if I like to devise a protocol which may get a place in IoT scenarios, then first thing is that I will basically leave aside the traditional that security solution. In traditional security solution will help to resolve that security problems in traditional applications. Now I need to focus that constrained application or constrained environment to have a secured application. Now then I need to make sure that what are the security goals for that constrained environment. Now suppose security goal is authentication and integrity, then a solution can be established with that challenge response mechanism. So two parties in constrained environment also, you can consider, instead of considering sensor node and actuator, one can consider that client and server. When you use COAP in constrained environment, then every node is considered as that either client or server. So two parties, for example, that prover and verifier. So verifier will ask prover, okay, what is your identity? Whether you are legitimate or not. Then prover will respond, okay, my identity is this. That is the typical challenge response protocol. Now if you extend that goal, instead of that one-way authentication, if you need that, it's two-way authentication or mutual authentication. Then if you want to extend that security goal, that after authenticating both parties that prover and verifier, they require to establish one transient key or one dynamic key. Then you need to again add one more communication, that first is challenge, response, then confirmation. Now this response will use some that security state which is known to the prover, and this X is also known to the verifier, and this challenge and variant of that challenge. So those will basically provide the information to the receiver that okay, you are talking to the right person. Now when I devise a protocol for that constant environment, then first thing is that I need to basically see what is that application security goal. Now for example, that application security goals are basically these four properties or four attributes. That privacy preserved data, which will avoid that tracing; authentication preserved data, which will avoid that impersonation; integrity preserved data, which will avoid data alteration; confidentiality preserved data, which will avoid unauthorized access to the data. Now I am not considering that other important security property, that availability of data. That again one has to consider in addition to these four that security goal. Now if you consider availability of data, again you need to make sure that if it is blocked, then the communicating party should get one immediate response or alarm, so that it will not keep its own state, memory state, to be active. It will just discard that connection and go to the other entity. Now let me show you that first, means how one can provide that privacy preserve. Suppose privacy is the goal. Assume that prover has that secret key and identity of the verifier, and verifier knows again the same secret and identity of the prover. Then here prover sends challenge. Suppose prover wants to first verify the verifier. Then verifier sends some parameter, dynamic parameter, which involves the key and identity of the verifier. And from this parameter, means other than prover, no other party will be able to deduce that who is in the communication phase. So it will not reveal the identity of the communicating party. Similarly, here prover will compute one dynamic parameter with that suitable means primitive. So you can, it is again up to the designer's choice. Means there are many primitives, crypto primitives available. One can use one suitable crypto primitive and can compute this dynamic parameter, again which will provide the identity of the prover. Then here that verifier, if verifier is going to authenticate the prover, then verifier is going to compute this. But important part is that from CR, the response from verifier, and CT response from prover, no information can be deduced about the identity of the prover or verifier. Now, so that privacy, where you can use that privacy in IoT scenario application, home appliances, transport, e-governance, social networking, defense, you can have a long list which will basically demand that privacy property. Now, in addition to privacy, now if you want that authentication preserved data and integrity preserved data, then the same design one has to just extend to achieve that authentication and integrity features. Now here that how to extend, again that CR is here. From CR and CT, no identity information about the prover and verifier reveals. Then here is basically again one more computation. So that now CR dash, so here is the verification. When after receiving CR, then the prover is going to verify whether at the other side the actual verifier is there. So it will compute the same operation, then it will check whether CR dash equals to CR or not. If that means if it doesn't match, then it will simply terminate the communication. That means other end the actual verifier is not there. If CR dash equals to CR, then verifier authentication has been achieved. Now that prover will provide its own parameter, that is CT. Now again same thing, at the verifier side, verifier will compute CT dash and it will check whether CT dash equals to CT or not. If CT dash equals to CT, then the verifier authentication is also on. So here from CT and CR, identity of the communicating parties are not being revealed, and both verifier and prover, they can authenticate to each other. Now you will find again several applications which require these three properties: privacy, authentication, integrity in the context of IoT applications. Suppose that application requirement is something more: privacy, authentication, integrity and confidentiality. Whatever that important data needs to be transmitted in between verifier and prover, so that important data must be protected from unauthorized access. So in that case, again the same design, one has to do some more operation. Now if you look at this means protocol design part, in the first part again less operation, but goal is only privacy. In the second part, one more communication and two more operations, and goal is privacy, authentication and integrity. And suppose goal is to achieve privacy, authentication, integrity and confidentiality, then in addition to that previous design, that this computation needs to be computed at both prover side as well as receiver side. So both prover and receiver, so they have to compute on transient session key, and with that session key, that important data will be protected between prover and verifier. So only this computation needs to be computed at prover side and verifier side. So that computation will again require that security parameters, a keying material known to prover and verifier, some dynamic or random parameter which will make that session key is temporary and random. Again, you will find several applications which require that privacy, authentication, integrity, data confidentiality. Now, if you want to add, suppose in addition to these four security attributes, if you want that, okay, that is that mission critical application, so availability of data must be ensured, that is important. Then you have to provide resistance to that denial of service attack. So in that case, now if you go with this design, then the first two that communication exchange, first two exchanges should ensure both prover and verifier that this data is not flooded by some attackers, or this data pattern is not having a malicious intent. So that both verifier and prover need to ensure with means as early as possible. In the first two actions, both prover and verifier will be able to means decide that okay, it is not denial of service attack. Then it will go to the next step, which requires some computation and some more verification. So that design of that security protocol for that constant application means will have several alternatives, but one alternative will be that final design if that alternative is proven secure. So that can be done with that by considering the adversarial capability or adversarial model. Means what model that application is considering, or what is the capability of the attacker that application is considering. Now again it depends at which layer you are basically thinking about the attacker. For example, application layer, one has to consider that attacker can do many things. But when you consider say link layer, then you can consider that attacker can do only this limited operation, not all the operations which attacker can do at the application layer. So here assume that adversary is capable of intercepting communication between prover and verifier and can inject data, can alter data and delete data. Now for this protocol, assume that adversary can execute some queries like send prover, send verifier, and attacker can corrupt some provers. And attacker can also capture some nodes and it will try to impersonate say the nodes which are not being captured. Now here goal is that attacker will gather some knowledge from that real execution of the protocol. Attacker will have knowledge of other nodes that security parameter. With this knowledge, attacker will try to gain from the nodes which are not being captured. Security claim for every set of inputs, the result of a real execution of the protocol with adversaries should not give non-negligible advantage in the security parameter of the keying material. So attacker with that adequate information, attacker will not be gain any significant advantage from legitimate nodes, and that's whether it is significant or non-significant, so that must be measured with the security parameter of the keying material. So that security is guaranteed if the protocol is sound against reasonably acceptable adversarial model. So that is very important. So that adversarial model must be reasonable. Then privacy of the protocol, again it will have that learning phase and challenge phase. So learning phase, again attacker will basically gain all sorts of knowledge. And challenge phase, attacker will be given suppose 2 CT or 2 CR. Then if attacker can say that okay, this CT belongs to some corrupted node or this CT belongs to say nodes which are legitimate, then that protocol will be insecure. So attacker will not be say anything about from that CT, whether it belongs to the random world or it belongs to the real world of the nodes. So here that there are two challenge phase, that two experiments. One experiment will involve that real node and security parameter, and another experiment will involve say random, instead of that actual secret key it will have a random parameter. Then from this experiment, say one that PB with real prover and this is PB with random prover. Now here adversary will be given P1 and P2, then adversary has to answer whether P1, P2, that means whether this means PBT belongs to real or this PBT belongs to the random. So basically this outcome of these two experiments are indistinguishable. Attacker cannot distinguish okay, this experiment involves the legitimate nodes or this experiment involves the random nodes. Now, for every set of inputs, the result of a real execution of the protocol with adversary is computationally indistinguishable from the result of a random execution with the adversary. Now, privacy is guaranteed if the adversary cannot distinguish with which of the two provers he is interacting through a large set of gathered queries. Now, when you propose security solution, that efficiency is also equally important, and particularly in the context of constrained environments. So one has to basically say that whether that solution is efficient or not, so that can be evaluated experimentally, that can be evaluated analytically. So here is one analytical illustration. So assume that on a constrained chip, the implementation of that signature takes roughly 10,000 gate array, gate equivalent. Then AES encryption takes say 3600 gate equivalent. Hash algorithm takes roughly 8000 gate equivalent, and say some other arithmetic like elliptic curve point multiplication take this operation. Now, with this, that information, that proposed protocol may demand this. For privacy preserving feature, that proposed protocol will take 5600 gate equivalent at prover side as well as verifier side. Then privacy authentication preserving will take roughly 9000 gate equivalent. Then privacy authentication confidentiality would take 11,000 gate equivalent. Now you will, at present scenario, we have RFID tags, we have sensor nodes which are well capable of handling this complexity. Now in conclusion, so I would say that the reality of IoT is not far around the corner. Enormous scope, challenges and opportunities. Internet along with high-speed mobile communication would become communication backbone for IoT infrastructure. Manufacturers, service providers need to agree on a set of solutions based on functional and financial goals. And security, privacy issues need more emphasis on constrained environments, because traditional security solution may not be a right fit in some constrained domains, which requires research progress in lightweight crypto primitive, for example, elliptic curve and based signature, elliptic curve based encryption, or arithmetic, lattice based arithmetic. So those are being treated as lightweight. So one can consider that instead of going with that conventional security algorithm or security solution. Proxy security, data ownership, because services as well as data are going to be resided in proxy or some other third-party servers. So that ownership issues must be addressed. Then denial of service, and means in recent that adversarial goal is not to gain anything, to means destroy the data. Means it will not gain anything, it will just encrypt the entire application so that the service will not be provided and the attacker will demand some ransom. So you give that, then I will provide the key by which you can decrypt that. So the denial of service, lock unlock service and destroying data. So those need enough attention from the scientific community. And finally, so that security and privacy issues are to me perhaps the say one of the biggest bottlenecks to have IoT in desired shape. And finally, regulatory issues, political factors have to be resolved to see IoT in its desires. With this, I conclude this talk. Thanks for your attention.
Hi, just a show of hands. How many Mishras are you? None? I can't believe that. Okay. I assume there's no bud. So I was going to argue that for Mishra I had K on it, which was large K, but for bud I didn't have one. On the other hand, if I was in Madison, Wisconsin, I would have lots of buds, but no Mishras. So, but Bud Mishra is not my name. I mean, not the one that was given. My real name is Bhuvaneshwar Mishra. For difference and privacy, we removed Bhuvaneshwar to Bud. So the question is, how revealing is the name? From my name, you can tell that I'm from Orissa. It's unlikely that you would have a first name Bhuvaneshwar. And it's also fairly easy to guess that I'm a Brahmin. And I was probably, my ancestors were probably brought in around 1000 AD when Orissa moved from Buddhism to Hinduism. So we are Kanauj Brahmins. And actually, if you go through the other markers, you will know that my Gotra means go is cow, Traya means shed, my cow shed is Bharadwaj, and I came from somewhere from the northwest through the Swat Valley, Saraswat. So there's a lot you can tell from my name, right? So, what does that mean? So what does that mean in terms of my traits? What I look like? What these recessive mutations I have. I live in a society that is a mixture of 4 different populations. The original Austroasian, which came over 65,000 years ago, then the Dravidians, and then about 10,000 years ago my ancestors came, the Indo-Europeans, and there was another one from the northeast, Tibeto-Burman. We took all of that and sliced them into 4 slices. So I'm an upper class Brahmin, and there are warriors, there are other classes, the business classes and the lower classes, and we forced endogamy. That means up until me, nobody in my few generations before me had married outside those 16 shasans. So we are highly endogamous inbred population. So we have recessive disorders. But because of that, India is actually genetically an extremely interesting experiment. As Dobzhansky described, the grandest genetic experiment ever performed on humans. Right? So what do we know about ourselves? Especially just one person. Take yourself. Right? You can go look at if you're female, from your mitochondria, if you're male, from your Y. We could tell exactly where your ancestors came, and what they moved through, and what traits you will have. So that's become an interesting data question. It goes beyond your social security number, your first name, last name, your age. It's an interesting set of data that's encoded in it. It's not encoded just you, but your ancestral history. And for humans, it's an extremely interesting structure. If you're Irish, most likely you are a descendant of Niall of the 9 host nations. If you're Chinese, you're most likely a descendant of Genghis Khan. Right? So the history has written itself into our genome, and that data is huge and hugely interesting because you can tell the jokes I will like, the way I will laugh, lots of things, completely trivial things about me from some of my markers, my skin color, when I'll go bald, when I'll have early onset of diabetes. A lot of these things are very interesting data analysis questions, but the data is still inside me. So for me, so something like that on the top is what is being proposed. Somebody will take with a sequencer, will take base by base, 3 billion base pairs of my genome, and then they will align it. They'll compare it with a reference genome, most likely to inventors, or If they want to, they could compare it with Jim Watson or Bishop Tutu or Bishop Tutu's son. There are only a handful of references. Remember, I'm a Mishra, I'm very endogamous. Most of my cousins are here. Right? I have very little to do with great venture. But that's what will happen. And they will call all the variants. Every place differ. A single base pair mutation, or indel, or a structural variant, or a copy number. And that will, either some of them will get interpreted, but will move over a long distance openly to a cloud. Okay? There is nobody else, at least if I'm in New York, there is hardly anybody else who is similar to me. I have no care anonymity. Every marker can be interpreted, and every marker will tell something about me. Does it make sense? And there are lots of rules about what can be done. There is HIPAA compliance, there is informed consent, there are lots of ethical ways you can handle data, but the data is open. So what we have is something else where instead of the model, the reference sequence, being sitting somewhere in the cloud, moves right to the sequencer. Right? So all the interpretation happens as you read, base by base. So all those things, error correction, base calling, alignment, variant calling, data compression, and encryption, all of them happen right at the sequencing mission. And that's what I want. So nothing, very little, moves to the cloud. And when it moves, the interpretation is already highly encrypted. And that can be done. It's not actually very difficult. So that's one of the things that we need to solve if we want a genomic future. So it's actually a very computer science problem. Okay? But remember, I said that I did not marry within the 16 villages I'm supposed to marry. My wife happens to be half Italian, half Jewish. My children cannot gain something by being compared to Mishras in Puri. Right? So what we would like to do is to be able to compare their genome to everybody. 7 billion people. Of course, we can't do 7 billion, but there's a very simple analysis called capture-recapture analysis that says if I can sequence about 10,000 people carefully, then that's enough. And the reason is that those genomes break into blocks. So from the ancestral genome, as they move around, they're recombined by breaking pieces of the DNA and recombining it. But they don't happen, the recombination doesn't happen arbitrarily, there are recombination hotspots. So what you have are this large chunk of over 30 kilobases of haplotype blocks, and the recombination happens between them. So even if there are 7 billion people, if I look at a particular haplotype block, say the middle one, there are not that many variations. So remember, there are 30,000. So in principle, you can get 4 to the power 30,000 possible sequences, but there are only about 7 to 10. Okay? So all of that data can be incorporated, can be compressed and encoded in terms of this multi-parite graph. So the nodes of this graph will be the haplotype blocks, and the edges between two haplotype blocks are the way the haplotypes are phased. Okay, so critical information about your identity is in the phasing, because you share your haplotype blocks with lots and lots of other people. And if you happen to have a twin, then of course you share, if it is identical twin, you share all the phasing with your twin. So you can get too anonymity by having a twin. So you can clone yourself. That's one thing. So so this is the structure that we will need to compare with in a general setting. So, and we want to keep it in a very compressed way and be able to do comparison to this. I'm not going to read through this, it's just a multi-parite graph. It has a set of blocks. In each partition, each block, there are a set of nodes. They are highly homologous to each other. That means they're similar to each other, but they have genetic inheritance structures within them. And every human can be described by tracing through a path through those haplotypes. Of course, there are humans, or potential humans. Those are paths in these graphs, but they don't exist. Right? So if I could arbitrarily make two people, maybe I can combine and create a new human. Someday you may want to genetically engineer a human, say I like this human, this baby, but I would like to choose 13th haplotype block from chromosome 1 and the P arm, Q arm. You could design things, but that's in the future. But you need to be able to keep all of that data. And I would like to keep all that data for 10,000 people in about 1 gigabyte of memory, so that it can go into a sequencing machine. It's about the same size as the memory that you use for taking pictures in any form. Okay. So one of the things that you want to do as you're reading somebody's genome, you get short strings, and you want to be able to do pattern matching very, very rapid. So there are two things you want to do. You want to count how often a particular pattern occurs. So for example, I want to see how many times BRCA1 gene occurs in this person's genome, or a BRCA2 gene with a mutation occurs, particular pattern occurs in somebody's DNA, because those will tell me whether this person has some, I could estimate the risk for this person to get breast cancer, familial breast cancer. Okay. So these are the kinds of questions I want to ask rapidly as a physician is sequencing through your genome, not wait for 7 days and send it to 23andMe and wait for 7 days and all that nonsense. I want to be able to do it rapidly and quickly and also not send ATCG out. I simply want to call the mutations directly. Okay? So the trick here is that this is joint work with Paolo Ferragina from University of Pisa of Ferragina-Manzini index reputation. So, of course, searching through the haplotype block stem cells are fairly easy because they are very similar to any other string algorithms you use, but the things between the phases, the things between the boundaries are the tricky ones, and the way you take care of this is to creating a dictionary index, which is very similar to FM index. So it's a mixture of FM index and levels it, because Ferragina-Manzini compresses with respect to repetitions, what biologists will call parallels, but also we need to compress with respect to homologous ones within the block. So that's where level sieve becomes important. So it's a mixture, very nice mixture of both of these compressions. And then you need, so once you have these indices, if you have a pattern, what you could do is to tell a range of suffixes that could match. Right? So these indices turn this problem into a geometric problem, and it becomes geometric range queries. And since I'm combining 2 or 3 things, they become geometric range query questions in 3D or 2D. Okay? So that's all you need to be able to do very fast search through this compressed data search. So I already said this, I'm not going to go through this, but then there are lots of different things you can do depending on what you are trying to optimize. We're doing IO efficiency. For decay, that's for the nodes, you use string B trees. For suffixes and prefixes, you use string B trees. And then I use external memory range trees for these geometric queries. On the other hand, if you are interested in compressed space, then you can use FM index, 2 Patrician trees, and range tree. If you are interested in IO, you can use geometric Born-Wheeler transform, string B trees, etc. So there are lots of designs space here where you can optimize how you're going to look at the genome and do this rapid pattern matching as you are reading this. Does it make sense? Okay. But this is not the only use of stringomics. This is what we call stringomics. They can also be used for transcriptomics. That means instead of looking at your DNA, I'm looking at the RNA that are expressed, and I'm mostly interested in counting how much expressions exist. And for multiple isoforms, for population genomics, and one of the big application areas is, of course, oncogenomics, the study of the genomes of the cancer tumor. How much time do you have? One range? Okay. Half an hour?
And you will finish at 4:20.
420, okay. All right, I'm fine. One of the other things is in epigenomics, where parts of your genome can be methylated or otherwise transformed without having any mutations, can also have various effects. I'm not going to go in. It's also used by other people for text mining, text searching, all sorts of other things. That there is a package called Femto that does some of that. It's actually developed by the U.S. government, so don't ask me why. Okay. So this has multiple applications, but what we are interested in is to essentially keep large sets of strings that have lots of common variations and be able to search them in real time. Right? Traditionally, you would have taken that corpora and broken them into some sort of high-dimensional multi-state hidden Markov models and create a probabilistic thing. This is saying don't do that. Take the data, just dump it into this compressed thing. And as you search, you estimate the state and estimate the probability of what would be emitted, because the data already has that. And this is something that I think will become common. I mean, another analogy would be, I already know all the jets that will come out of Large Hadron Collider. I should build that model and just filter that out and only send things that could be a Higgs boson. Don't need to send all the data. So this is completely going against big data. I don't want to see the picture of cats. I don't want to see the picture of your fried chicken. They should be eliminated the moment they appear, because they're not interested. So most of that model should go right into your smartphone and will be deleting big data before they become big. Right? So this is going to a small data and moving the models to the machine and only looking for interesting phenomena that are important. And that also connects very well to privacy, intrusion, all sorts of security issues. Okay, so the next question is, how do you detect this in real time? And the idea is very simple. So remember, the classical mechanism was the sequencing machine that did a base calling based on some base and prior that describes the chemistry. And then those base calls cuts into little strings and they get aligned, etc. Here what we'll do, as you base call, they get aligned and they predict what the next base is likely to be. Because I already have the reference, so I can, if I have 10 base string, I align it on all the places, I predict what the next base is going to be. And my prior is a combination of the chemistry and what the reference sequences say the next base is likely to be. And I'm going to optimize that score. And I'm going to optimize that globally. This is a little bit of a technically tricky question, but people do this on alignment using Smith-Waterman, which was actually developed for evolutionary distances and don't apply to the chemistry in sequencing machine. So if you want to optimize those things globally, you actually have to look through all possible strings. So if I'm looking for an n-length strings, I actually have to score all 4 to the power n. Okay, for n equal to 30, it's already billion, or more than 2 to the 30 is billion, so it's a lot bigger than that. So how do I do that? And the idea was to do branch and bound. Because most of the alignments will turn out to be false and can be eliminated at a low score. So with a little bit of branch and bound, you can get very high accuracy. So this is from results that are about 3-4 years old. Basically what it says that if you look at the sequence reads, the best one that you can get from Illumina, and also there is another one from Europe called IBIS. Those are the green and blue ones. And we can get the accuracy up to about 120 bases, while those essentially stop around 80 bases. So the technology, the chemistry hasn't been changed. Only by changing the algorithm, I can create long DNA strings. So here is the idea. So I'm in the kth cycle. There's a chemistry going on, and I want to predict the base is B. So the conditional probability of B given x of k, you use the Bayes rule, and if you factor that out, I only have to look at probability. I need to know what is the signal going to look like in the kth cycle. If the base is B, what it's going to look like if the base is not B. So base can be A, T, C, or G, and not B can be the complement of that. And because I'm aligning it, I have to have some marginal distribution, estimate of marginal distributions, that in the kth cycle I'm looking at the base B or not B. So one part of the score is coming from the chemistry of the sequencing machine. The other part is coming from the priors in the reference. And that's basically the function. And this is branch and bound. And this steals the pattern matching data structure that we have to actually do real-time search for pattern matching as it prunes the tree. So at each point, I can compute the score very efficiently just by looking at the match using the data structures that we create. And that improves the efficiency and accuracy and the read length. But also, I'm going to skip all of these. This shows that it works better than anything else these days. The other thing is that all of this can be implemented in a field programmable gate arrays. So all you need to do is to take this hardware and slide it into the sequencing machine. Okay. The same story also holds true for RNA, but I'm going to skip it. Okay. Just want to tell you a few more stories instead. So in RNA-seq, the problem is that there are lots of unannotated genes in the genome, and this sort of alignment makes it very difficult. So you need to dynamize the data structure, and we can show how to dynamize it without losing any efficiency. So there is a garbage collector like state that keeps rebuilding genomics every few steps. So it's basically a learning algorithm. So I'm going to skip all of this. This is actually described in great detail. So, going back to the big story, what is genomics going to do? What computer scientists are going to do for genomics? So, there are lots of steps involved. Of course, some of the steps do not relate to anybody here. Key step is sample preparation. So a lot of the interest in research is going on in how to work with very small size samples. One example is there's a lot of interest right now in circulating tumor cells. So long before you get cancer, some of your tumor cells are actually circulating in your blood and urine. So if you can fish out those tumor cells and sequence those, you may be able to tell what cancer you may get in 4 to 5 years. And if you can do epigenetics, which is much harder to do, you can even tell the tissue of origin. You can tell this is going to be breast cancer, this is going to be glioblastoma, this is mesothelioma, etc. So, but that requires very precise, exquisite sample preparation for single cells, for cell-free DNA, for single molecule technology. And it's an exploding field. And we have done a lot of work on single molecule. The next thing is sequencing, which is sort of not moving very much, but people are very excited about it. And the third step is bioinformatics. How do you take that data and understand and interpret? And the last step is being able to tell from large-scale, large population studies what exactly can we tell about many of these disorders. Primary ones are in cancer. There are similar questions about behavioral diseases such as autism, bipolar, schizophrenia, and also the whole range of things starting from post-traumatic stress disorder to anxiety to neurodegenerations to Alzheimer to Parkinson's. So all of these things we still don't know. We have very little idea of what's going on, even if you can sequence the humans, the DNA, the tumor, the dog's tumor. So we can do all of that, but the interpretation step has been a big challenge. So so everything I said relates to that. So I'm not sure how much you know about genomics, but I'm sure since you are not living in a bubble, you must have heard something about it, and it's usually described as a very big success story. And I want to challenge that story. So, and tell you why genomics is an exciting subject. especially for mathematicians, statisticians, computer scientists, systems modelers, systems biologists, etc. So here is the story. I tell these stories as Greek tragedies or the Greek myths. So there are three characters: Prometheus, that's how biologists look at themselves; Sisyphus, which is the story of genetics; and Tantalus, that's the story of computer scientists. How many of you know who these guys are? Prometheus, Sisyphus, and Tantalus. So those are my three favorite characters. So the Promethean story, that's Prometheus. So he tries to reach to the sun, etc., but his wing melted or something, so he's back down. So the Promethean story is that we have stolen God's book of life. We can, we did Human Genome Project, we know 3 billion base pairs of genotypic genome, we know the 46,000 genes, we know the annotations, we know the HapMap, we know all the millions of single nucleotide polymorphisms that vary, we know the Mendelian traits, we know epigenomics, transcriptomics, microbiomics, not metabolomics, oncogenomics, etc. And in fact, we have built synthetic biology, we have synthesized life, ab initio, we can tell the future, we can do predictive, personalized medicine. All false. Why? In fact, the best we can do is this machine. It generates about, well, now it generates about terabytes of data in 8 days, but it generates in very short streams. And one thing you have to do to understand this reference genome is to be able to assemble them correctly. And that's an anti-complete problem. And the algorithms we have failed. So in 2003, because that was the 50th anniversary of the Watson and Crick's paper, which appeared in 1953, we declared victory by saying that we have a draft version of human genome. We still have a draft version of human genome. We have the 19th draft version, it's HG19. It's not yet complete. We do not have haplotypes. We can't tell your father from your mother. And we have lots and lots of structural variants that we don't understand. We can't actually describe correctly in the right order. And so that's a very complex computer science problem. And the main reason that we have this problem is the DNA is full of repeats. Right? So the theory to honor, which has turned out to be true, evolution actually does not occur by single nucleotide changes, base mutations. It happens mostly by duplications of long chain, big chunks of DNA. And that's the evolution by duplication theory. And what that means is that our DNA is full of repeats, and many of these assembly algorithms fall apart at the repeats. And the trouble is that you have a father and a mother, and they have the repeats, but they have different repeats, and you can't tell the difference between the haplotypic ambiguities from the repeats. And for that, you need slightly different algorithms, and the one we developed was based on the single molecule technology called optical mapping. On the other hand, this hasn't been yet fully used to create the 10,000 haplotypic reference sequences that I talked about. This was used nonetheless to correct HG19, and a similar technology from BioNano is being used to find more errors. Last year somebody from NIH gave a talk, and for the first time they admitted that there are errors. And the talk was called Keep Calm and Carry On. So we're keeping calm. So that's one of the stories. The other story is the Sisyphean story. So what is the Sisyphean story? That's the story of geneticists. Here's what you do. Our knowledge of biology is incomplete. We only have imputed haplotype phasing, lots of errors, and there are lots of genes that we don't know, etc. So what they do is, say for example, I'm studying autism. I will get 20,000 probands. So 20,000 probands would mean an affected sibling, an unaffected sibling, the father and the mother, the quadrants, and I will get say 20,000 of those families, say Simon's family. So there's data like that. And then I'll postulate that it's a de novo mutation, and I'll do some data analysis, and yet, at the end of the day, it will turn out that there was multiple hypothesis testing errors, I did not phase them correctly, and I got something wrong. So next year when we start, the sequencing machine costs are reduced by a factor of 2 thanks to Moore's law of biotech. And now the person who gave you $10 million has made $20 million. So you restart. But now you have 80,000 probands. So your stone has gotten bigger, but your answers haven't gotten easier. And there's lots and lots of difficulties. Some of them are multiple hypothesis testing problems, but common disease, common variant hypothesis. But there was an article in Scientific American that described this issue and said revolution postponed. So this genomic revolution that we have been waiting for has been postponed. So I took a vacation and I'm here having fun. And when the revolution restarts, we could go back. And the reason is this picture. So not all humans are a single population. In fact, if you do any study like the Danish are doing with 34,000 males because of male infertility, or the UK is doing UK 10K, it's hardly useful because one English is not very different from another Englishman. They're more or less clone up. And to understand that, you have to see that we started somewhere in the Rift Valley in northeast Africa. There are 2 other populations, L1 and L2. L1 are the Hadjas, L2s are the Kalahari Desert people. They speak Khoisan. Khoisan and Hadza have clicks. We don't have clicks. We don't speak our language with clicks. And we were sort of stuck between the water and the Sahara. There was an attempt during the Green Sahara for a small group of people to go to Israel and establish a Shul Valley population. But something happened, something very small number, about 120 people, very courageous people, crossed Bab el-Mandeb, that's the place that connects Ethiopia to Yemen, and they crossed into Oman. Oman is not a desert, it's actually highly tropical because of monsoon. And from there, they crossed over Iran and Iraq, which was the sea level was much lower, and they came into India. From India, as you can see, they went to Sunda and Sahu, so those are Indonesia and Malaysia, into Australia, Tasmania, and New Zealand. That's the Mongolic population, and our Australasian population, some of them live fairly close to us.
Why dotted line?
That's I'm not sure why they're dotted. They're pretty well established structures. Maybe the markers are not here. That marker that came from L3 is M. So we carry, well, not we, but most Indians, Australians, they carry that M marker. And there was also another wave back. So China has had 2 waves, Europe has also 2 waves, and just 2 out of Africa waves. So what that means, that's why I told my story in the beginning, it's a very complex stratified population structure, and you have to worry about yield Simpson effects in interpreting genetic data. So you need to do population stratification, either because you understand the structure of the population from record, or you need to do haplotypes to understand how the fathers and mothers and children are related. And we haven't done that. That's why the genetics has been a hard subject. So it's not a question of having big data. It's a question of having right kind of data. So we haven't done a very good job of that. And the Tantalian story is us. We are the Tantalists. There's big data. We are drowning in the data. So there's data up to our throat. And there's a low-hanging fruit. Right next to our eyes, we are chained. We can't drink, we can't eat, we are dying of thirst and hunger. So here is our picture. A picture of Tantalus suffering. That's what we look like. And the reason is there is people have talked about Moore's law. So that's what the biotech has been doing in terms of throughput. So around 2007, it actually almost quadrupled. So instead of every 18 months, every 5 months, we double the amount of data we can collect. So that's biotech's Moore's law. In computer science, for CPU, it will be about 18 months. The original Moore's thing for data storage, it's about 24 months. So now imagine we are going to create double the data every 5 months, and you guys, the computer scientists, can create storage, double the storage every 24 months. So that's creating, so that's not a situation that the Moore's laws are matched. Of course, we have mismatching Moore's laws in computer science, the way memory doubles, the way CPU doubles. They're not completely synchronized. That's why someday we have all our computers on the cloud, someday we have it on the desktop. We move back and forth because of this asynchrony. But here there's a completely difficult, impossible asynchrony. And we have cloud data deluge. Cloud computing is not going to be able to be helpful. And the low-hanging fruits are not quite achievable without fixing those problems. So one of the issues is that we talked about in total color is to actually not worry about the data deluge, just don't store all the things, to move all your processing as close to the biomedical applications. So this is called Kreiger's law for data storage. So the other thing that I find amusing is this is a list of, if you go to Wiki and look at all the assemblers, this is a full list of all assemblers about 2 or 3 years ago. So this is the problem of taking small reads and overlapping them and stringing them into a superstring so that every string is a substring of it. So it's the shortest common superstring problem. And if you look at it carefully, there are many different kinds of algorithms. The OLC algorithms are almost all before 2007, and there are some greedy algorithms before 2007, but almost all of them, seed and extend and sequencing by hybridizations, are after 2008. So the way we responded to the data deluge is by designing lots of really bad algorithms. And no two of them agreed to use the same algorithm, right? And here's an analysis of kinds of mistakes these algorithms do, and they all make all kinds of mistakes, but fortunately they're not correlated. They make all kinds of different mistakes. So what you do is if you do your DNA and send it to different groups, you'll come back with completely different interpretations because they all make different kinds of mistakes. So I'm not saying that if they make the same mistake, it's going to be progress, but that's the situation now. And there are ways to solve it by going back to the core problem and trying to solve it better. So there are some algorithms work we have done, and there's ways to solve these problems. So this algorithm is called Sutta, which I like a lot because Sutta means thread and also means formula, an algorithm. So the DNA is both a thread and an algorithm. Anyway, so going back to clinical genomics, so if I want the physicians to do genomics, to actually interpret your data quickly and use it in medicine, we have to address all sorts of problems. There is hardware problems, because we're on speed. There's data compression problems and security and privacy problems. There's a lot of these problems need to be solved before any of this data can be used in practice. It's not just a question of accuracy and correctness and solving any of these problems, but it's a full range of computer science is going to touch. This is my other pet project, to create 1,000 rupees genome, because $1,000 genome is nice but not available. And so that's about $23 for 6 billion base pairs, and it's about $135 billion in US economy, which is less than what we spent in Iraq. So, and actually it can be designed and built. It's not that complex. Again, I'm going back to the story I said. If we can do $1,000 genome, the best project would be what Dobzhansky called the the greatest genetic experiment ever performed on human. Maybe in another generation or two, the endogamy will go away, and the structure of the Indian population will be very different. We'll learn a lot by understanding these populations. And there are some populations, like only a population in Andaman Island, which may disappear. There are only about 30 or 40 people left. And there's strong founder effect, there are lots of recessive diseases. And also these are very, very challenging for the kinds of genetic analysis that we want to do. Remember the problem with multiple hypothesis testing and Yule-Simpson effect. They've become extremely critical for the Indian population. Unfortunately, unlike China and other European countries, India seems not to have done anything. So I would like you to go and argue that you should build a cloud, build lots of genome centers, and combine the data, etc. And lastly, I want to start by saying thank you to this man. His name is J.B.S. Halden. How many of you know who Halden is? Okay. He lived very close to here, so you should be ashamed. So J.B.S. Halden was among the most famous mathematical geneticists, Halden, Fisher, and Wright. He is probably the most prominent scientist, mathematical quantitative population geneticist of the same caliber as Darwin. He got angry with the British government. He was a Communist Party card holder. He over Suez Canal. He resigned. He gave up his citizenship and moved to India. He went to Calcutta, Indian Statistical Institute, and the head there was another headstrong guy, Mahalanobis. And Mahalanobis and Halden had a big fight because Halden was away. Kosygin from Russia was visiting Calcutta, and Mahalanobis showed Halden's lab without his permission. And the Prime Minister of India, Nehru, was called to solve the problems between Mahalanobis and Halden, and Nehru, not knowing what to do, called an Oriya Chief Minister, Biju Patnaik. Is actually the father of the Chief Minister now, Naveen Patnaik's father. So he built an institute in Bhubaneswar and brought Halden. And Halden actually lived here until he died. And he said he would like to be remembered as a man who in his last year founded the famous Bhubaneswar School of Biology. Unfortunately, it doesn't exist. He did try. And he said you can't do that by ordering people about. He wanted to build it up from ground up. And he worked very hard to do it. He also said something interesting about Oriya people and Bhubaneswar. This place has a very pleasant climate. I'm sure you guys all agree. And the people are highly civilized. So if you are in Oriya, feel proud. People here tend to be rather unadventurous. However, some go in for flying, communism, and mountaineering. Not to mention dangerous driving of mechanically propelled vehicles. Failure to acquire a driving license adds to the fun. So those of you who are going to take a taxi to the airport, remember Halden. So Oriya taxi drivers may not have their driver's license. I stopped.
So what there are several technology enablers now which make this actually something which is an idea that whose time seems to have come, and that is that you now have smartphones which are cheap and widespread across the population. Even in relatively poor countries, you have a very wide spread of smartphones, and they come with a lot of compute power. Apocryphally, the smartphone that I have in my pocket has got more compute power than the computers that took the man to the moon. And they're used for very useful things now, like posting cat pictures on Facebook. So you got cheaper and portable sensors now. Earlier it took a lot of money to do an iris scan. Now you can do it for basically the camera on your phone could do a pretty good job of taking a scan of the back of your retina. There are cloud technologies, and we heard a bit about those. Nikolai also did talk about some of the issues that go into managing the storage in there and computing in there. And you've got much better networks which are much more diffuse. So you've got telecom, which has really made things possible which earlier you couldn't have even thought about coming up with this kind of solution. So what is the solution really doing? It's moving collection of information about patients or people who are just monitoring their health even if they're not ill, you're moving it closer to the patient. You're taking it away from the hospital and moving it out towards the patient, pushing it out. And what does that come with? It comes with the potential to really make healthcare cheaper by reducing the costs of people having to go to hospitals and use expensive equipment, often to find that there's nothing wrong with them. That's one thing. And also you can probably get much better healthcare by making sure that you don't have to move very sick people to the hospital when they can't be moved. And I would like to mention this word better again, because the most interesting book I read in the last 12 months, or the set of books I read, is by this Dr. Atul Gawande, and very thoughtful, one of the great thinkers of our time, public intellectuals of our time, who writes for the New Yorker, and he's written 3 wonderful books, and one of them is called Better. And he's concerned about how to make healthcare delivery better. So I want to say better is really important. And even if you don't buy the book Better, do buy the checklist manifesto. It'll change the way you work. So one thing which we noticed in all these healthcare solutions for smart healthcare was that there was a similar set of ideas which seemed to work very well, maybe in different scenarios in the rich world where people are monitoring, wearing Fitbits and monitoring their wellness, as well as in the poor world where you have a rural health worker walking around a village and taking readings of 100 different people. So that's basically what got us some funding for a small project that we were doing. So I'll just walk you through a typical healthcare scenarios. So this is the one which is in, and I must thank my student Chandrika for making up these slides. So healthcare worker Hina goes to a patient Pooja and gets her hemoglobin reading in the village. Right? She's taking a mobile kit and she goes there. She takes a reading from a portable device. Maybe it's connected by Bluetooth, maybe it's connected by USB. It goes to her PDA. And now we can actually get these PDAs. These Akashas actually work. The third iteration of it, about 2,000 rupees a tablet. Right? You can actually get it to her PDA. So that's the reading. Just follow the red dots. It goes there, and now it's on her PDA. And it's just with this healthcare worker who's maybe managing 1 village, 2 villages, or whatever, going around taking readings of various women, children, and so on. But this could be connected up because of communication technology to a remote hospital. And so using certain information which has been collected can go up through this thing called the internet, and it goes to an electronic medical record that's sitting in a hospital. I'm taking my time walking through this because I just want to get this, the fact that it's very, very distributed, this system. And engineering it is, you can't build one solution. You have to actually be very flexible in what you have to deal with. So the data has come and now it's sitting in a hospital. It seems to be ordinary communication going out there. It's sitting out there, and now I've got my hospital out there. So I've got my data out to the hospital using standard technologies. And it should be easy to engineer. You build an app on the phone, you collect it, and you communicate out using some kind of messaging technology. But there's that hospital out there, and the hospital has got its own infrastructure. And so this information about the patient Pooja sitting out there could be accessed by a doctor. Doctor is called Divya. So Dr. Divya can see it on her PDA, and if it was an emergency case, she can deal with it and do something. Or she could access it, if it was not an emergency case, she might be accessing it on her laptop or her desktop in her office, and she can look at it and decide, whether this patient really needs some urgent care or something. So the information could go that way. This is internal. This is standard network technology inside the hospital. And then maybe she decides that Pooja needs to come in and get an ultrasound done because the fetus in her runs some risk or something. And so the ultrasound technician is looking at it and can update, the report goes in, takes an ultrasound, the report goes up also into the EMR, needs to be linked up to the previous readings. And so all of this information flow is happening within the hospital. And then you could take the ritual scenario of another person, confusingly also called Pooja, but let's call her Preeti, if you don't want Pooja, but she's monitoring her health parameters, her activity and so on, and so she's got her phone and she decides to put it up into a patient healthcare record sitting on some company decides to run this as a business, and so her Fitbit and other stuff is just uploaded information about her activity, and that goes up onto the patient healthcare thing. Now this is very similar. You're using very similar technology to get it up there. So that's how the information is flowed. You can put these two together, and you can make 1 million copies of each and put them together, and now you have two different healthcare systems sitting together using very similar technologies. And you can link them up. You can take the patient healthcare record and you can say if Pooja needs to be in a hospital, she can transfer information from her patient healthcare thing so that when she talks to Dr. Divya knows how what her activities are and so on. So there's all that happening, and then there are also researchers like people who funded by WHO who want to know about all the pregnant women in this particular state, what is their hemoglobin level, what is their activity level, what are their various other things happening to them. So there's Dr. Rita out there who signed some kind of agreement with the hospital and said, well, your healthcare records I want to do some analysis on them. And so these healthcare records are somehow massaged, turned into something anonymized and made accessible to Dr. Rita, who runs the analysis and publishes the papers and stuff. So this is, you take many copies of this, and this is a plausible healthcare delivery system which depends on mobile devices and sensors out there with the people. So that's the sort of scenario that we were trying to build a little prototype of and see how do we build the various pieces. So here were the requirements, and I'll just very quickly say that for this to work, what you want this to be very easy to use by people who don't necessarily have a lot of training. You want to be able to integrate various kinds of sensors into it. No point in building an app for hemoglobin, a separate app for your heart rate, a third app for your some activity and so on. It should be sort of a plug-in and play. And there are groups which are building this. There's a Swastis slate by the Public Health Foundation of India where you can take a tablet and link up some 11 different sensors can get linked to it. It's good. And these things can get pretty inexpensive. $100, 5,000 rupees, you can get a fair number of sensors and a tablet. And what makes it work is that all these pieces of information which are collected should be in some kind of exchangeable format, and XML is a solution to it. Why not? People will argue and say this is better than that, that's better than this, but once you come up with a standard, you now have a lot of information which you can collect, analyze, take decisions on, and so on. So this was one of the requirements. If you look at the data, and in the first day, the V's of data keep getting mentioned, right? There's a huge volume of data. If you really get this going, there's an enormous volume. There's a lot of variety. The data is going to be very different. There are all kinds of data that you're collecting. There's an issue of velocity if you've got streaming sensors, if you're taking ECGs, you're wearing those halters and walking around. There's a lot of velocity possible, especially in hospitals. But much more important, there's this veracity and how good is that data? Can we rely on it? Can we do is the researcher's research going to be valid if the data you collected was of dubious quality? So you don't want terabytes of data which is of questionable quality. You really want some kind of validation of that data happening at every level. And and the people who are giving up this data probably don't want their information all over the place. They probably want it, if for no other reason, they don't want their healthcare costs to go up because the insurance companies say, oh, I know you have this illness because I have this data about you and I'm going to double your insurance rates. Or they don't want someone else getting to know that they have a particular condition or that they went through a certain procedure because that is socially or something awkward about that information. So here are the engineering challenges to this system. In building such a system, you don't realize there's a lot of mobility in the system. People are moving around, the devices are small, they're mobile, the aggregating devices, the phones are mobile, the sensors are mobile. There's a lot of things moving around, which is very different from the old hospital system. And this mobility actually gives you, poses very serious challenges to knowing anything about that data. In a fixed system, when you go to the doctor and the doctor takes data from the lab in the hospital, there's a lot of implicit information about that data's veracity, which the doctors or any decision maker relies on. You separate them with time, space, and you add in mobility. You cannot rely on those things. You have to really rethink what you're doing about what you know about the data. There's the issue of trustworthiness. These things are cheap. They can fail. They can give you bad information. So that's another challenge. How do you deal with things? How do you build the system? And it's possible that some percentage of them are not actually giving you good data. This communication is no longer synchronous, face-to-face. You probably have to build in tolerance for asynchrony being separated in time and space. Some data is going to be streaming data. The Fitbit stuff, you're streaming it to, especially if you're wearing a Holter, it's sort of sending your ECG to your phone might be processing it and sending summaries up there, but you have to deal with continuous data, you have to deal with discrete data, you've got a variety of data to deal with. There's a security issue which I've been alluding to, I've been mentioning it off and on, but integrity of the data is extremely important. If this is going to be any use, if the data is going to be any use, integrity is really important. But much more difficult to deal with are the fact that you're dealing with very different administrative domains. You're dealing with a phone which is administered with one set of rules, you're dealing with hospitals in which another set of rules come in. Two hospitals may not have the same, agree on what their rules are or what they do when they share data and so on, who owns the data. There's a whole set of policies where in India especially, but worldwide, the things are all over the place. It's not, these questions aren't settled. And no hospital is going to change its installed base, its system, just because we have a nice new design which solves the work. We have to work with this huge installed legacy. So these are all issues of scalability. Alright, so I'll very quickly try to go over the issue of how we go and acquire data. Right? And this is some work which my master's students Abal and Anju had built actually a little sensor stack. And I'm not going to talk about that, but just sort of tell you some of the things that we go through in acquiring data. So this was the architecture they had, and they built an application network stack where you can take stock sensors, connect them up through an Arduino board which aggregates them, uses Bluetooth or USB to connect it to an Android phone, and then there's these application network stack layers which gets it to a hospital. So there's a stack between the microcontroller board and the Android, and then there's the usual telecom network or Wi-Fi to get it across to the server. So they actually built the system. We can demo these. If you come to Delhi, we can show you how this works in a lab. So conceptually what's happening is that there's this very basic notion of an encounter, which was in the old days it was the visit to the doctor, and the doctor did a bunch of tests on you. Now it's diffuse. So the health worker is collecting a bunch of medical data from you using not just one sensor but possibly a bunch of sensors, and the correlation of the data they collected from the sensors is important. It's not that you build a separate app for your pulse and a separate app for your temperature. It's what was read together that is important. And what you're doing is not just collect data, but you're also collecting all kinds of metadata about whose data is this, who took it, when, where, why, how, using what devices, following what protocol. So that's also being recorded. All of that is easy to record using the cell phone as a provider of some of this information using various sensors on the cell phone, GPS, the accelerometers and so on, to say whether you're following a protocol and so on. So you can do a lot of things. And then into that sensor stack that my students built was a layer which would sort of validate. If you're taking temperatures, human temperatures, you expect it to be in a certain range. And if you get a reading outside that range, you say, no, this can't be quite right. Are you quite sure? You give feedback immediately to the person taking the temperature that I don't think things are quite right. Please retake the temperature. And it's possible that the temperature was abnormally high or abnormally low, in which case they can say that I'm pretty sure that I've done this right, but they get some feedback. So there is some level of validation and rechecking to check that the protocols of taking readings are okay. And then you're fusing data from multiple sensors, the sensor fusion that Kriti talked about, that you're actually taking all of this together and encapsulating them and packaging them, saying this is what the outcome that you're getting from one encounter with the healthcare professional. And finally you sort of push this out onto the cloud. But along the way there's further processing happening. And so it's not very clear what the, when exactly, it's not a discrete point in time that you say the encounter happened here. It's really an interval. And it can be quite spread out if your communication is asynchronous. So if you look at the electronic outcome of one of these encounters, it's a record with all kinds of things on it. What devices were used, what faults they have, what's the patient ID, who took the reading, when, where, why, what the value was, a whole bunch of things. And it's got both data. The medical data part is very, very small. It's the hemoglobin reading there. And almost the rest of it is just sort of crowded out with this sea of metadata that has come with it. And it's interesting that the metadata is of very high importance. If I just show you an X-ray, and we have no knowledge about whose it is, when it was taken, where it was taken, using what device it was taken, you don't get very much information other than saying, oh yeah, somebody's got a broken bone or something, or you take a sonogram and say, oh, somebody's got a baby inside them. On the other hand, if you know that it is the Duchess of Cambridge, you can make a lot of money right, selling that. So the metadata is actually fairly important, and very often you can piece together the metadata. That's what Katusha actually showed us. You piece together the metadata arrived at from different sensors and triangulate it. Maybe you do some queries across different pieces of information which have gone into your database and figure out this metadata applies to this data, and you can link it up. So that's one of the challenges. So one way of thinking about it is, okay, you can keep taking these records and you build a big collection of records. That is probably a very sterile way of looking at medical information. There's a lot of serious relationships. This patient's readings across time, across space. In this space, how many people tested positive for H1N1 or something like that. There's a lot of cross relations you need to do. And then there's a lot of meta annotations people keep adding to the data. The physician keeps noting things down when you go in. They take readings and then they keep making notes. So what does this really look like? It really looks like conversations. And I think that's a very useful metaphor to look at, how to look at medical records. It's an ongoing conversation. There's one thread, there are many threads. You can think of a person thread, you can think of a place thread, you can think of a doctor thread, and so on, about how there are various progressions of linking up various data records across. So it's not just a collection of discrete points, but they're very linked up. And you want to actually query these along these various axes. So the other thing is that there are many more principles involved than we realize. It's not just patient and doctor. There are health workers. There are relatives of the patient. There are people who make the bills. There are people who drive the ambulance and so on. There are lots of people involved. And more importantly, there are lots of non-humans involved. There are a lot of chirping in this conversation is due to the devices which are there. Your phones are putting in a lot of information into these conversations. There's a lot of structure happening in these conversations, and linear structures are probably very, very poor structures to look at. Tree structures lose correlations. DAGs have much more to say about how things are linked up. So and there are lots of relationships. There are causal relationships, there are temporal relationships, there are other relationships which we may not even imagine at this stage. And there are lots of analysis you want to do post facto. It's not always in the forward direction that you do things. You want to then say, oh, all of these people suffered from this thing, this was a treatment, and then 10 years later you find that there was something wrong with that drug. And what were the consequences of having administered that drug? So if you're going to build a rich thing and you're going to build it for 5 billion people or 1 billion people, you need to be able to architect the information system in ways that sitting here and a handful of people really can't imagine. And they can't build the system ab initio. They have to work with what has already been built and what. So just to tell you again, metadata matters. It's not just the NSA metadata that matters in snooping on your phones. Metadata matters here in very nice real ways. And what is the metadata? Who, why, when, what, where, which, all of these usual questions. And what does this metadata do? It really is giving you some assurance about the data that you've collected. And even if you're not using the metadata in a predictive way, you can use it in a post facto. I don't want to use the word post-mortem. You can do audit analysis. Now this is very much like what database, Peter Buneman and all did in the idea of provenance in databases. Except that you may not have very precise information. So you're using the metadata to give you at least some level of confidence in the data. Provenance is more definitive in answering some of the questions. Here you might not get very crisp answers, you might get more probabilistic or answers where you sort of give some weightage to it, some fuzziness to the answers you're giving. So very quickly I'll just give you some ideas of why metadata matters. Right? You can ask interesting questions without even asking about the data itself. Is the health worker doing her job honestly? Does she follow protocols correctly? You could probably answer some of these just by querying some of the metadata. Do others in the area also have the same symptoms? That's a public health research question. Is there a correlation between the weather and environmental conditions and a particular manifestation of high temperature that you're seeing in patients? is the device working properly? There's a particular device we gave out. Consistently, everybody's temperature is coming up, being more than 100 F, more than 39 centigrade or something. It might be just that the device, they're not ill, it's just that the device is bad. Or it might be not just that at a particular device, it just might be that the design of that whole range of devices has got a bug in it. So there are commercial issues, there are operational issues, and there are all kinds of questions that you can ask query about a combination of the data and the metadata. And if you didn't have the metadata, you wouldn't be able to do all of this. So just to summarize, there are a variety of questions you can ask on the medical data and the metadata, or only on the metadata, administrative questions, which have nothing to do with temperature readings. But how many readings did this particular health worker take in a month? Does she know how to use this particular device? And the questions that I don't know anything about databases. So what is the right language? What is the right framework? And I've been trying to get my PhD student to answer this question. What is a good query language for this? So, I get an answer, well, we could do it with SQL. And then say, well, are you sure you can do it with SQL when we don't know that these are going to be relational tables? Oh, no, we could do it with Sparkle, or we could do XQuery. We need some path queries. And so I keep getting a different answer from different people. So that sort of leads us into a question which I have no answers, and I would love to hear answers. How should the data be collected? In what format should it be stored? As I said, these conversations have got DAG-like structure. Should we use XML? Should we use RDF? Should we be going with any of these? Should we reinvent something? I don't know. What I do know is, What I do know is that there are certain things which we need to worry about in how we're going to store this and retrieve it, and we don't have a lot of flexibility. So the reason I put the Escher thing out there is that the Escher, this particular picture has got 3 points. It's a triangle out there. And I want to label the 3 points C, A, and P, and you will see in a minute why. Right? So before I come to that, let me just remind you again that if in that little trace that I did, there were red points all over the place. And these red points are pieces of information at various places. And it's not necessary it's the same piece of information going across. In going from the EMR to the EHR of the World Health Organization, the data records may actually have got translated, obfuscated, some pieces of information changed, and so on. So it's not necessarily that they are the same, but they've been transformed in some ways. And even one little encounter has gone and manifested itself or tainted so many devices and places and repositories all across the place. So one of the things is saying, what was in that particular encounter record, that reading which we took, requires us to have some kind of consistency across all of these. And there's absolutely no guarantee that the EHR or the EMR, the PHR are even going to be similar looking databases. One might be relational, the other might be hierarchical, one might be something else. How do we even address this issue of some kind of consistency? That's one of the things that is something we're grappling with. So that's what I want to say. Heterogeneity is what we have to deal with. We have to sort of make our design of a system keeping in mind that we have no real control about what people are going to do. What we can do is put in the metadata systematically and build the linkages systematically so that we can answer that question about what is the taint of this particular encounter record. How can I make it available to the different principals who are involved, each with their own little window of what they can see. So there's this view problem, and luckily I don't have an update problem. I'll tell you why. So Just to repeat things, hospitals are unlikely to change. They're not going to, if they've invested in a database, they're not going to buy a new database just so that they can fit into your thing. Relational formats are probably not very good for certain kinds of medical data. What do we use? I don't know. MongoDB, XML, key value store. All I know is that let's design for them to be federated, heterogeneous, and let's come up with some kind of flexible thing. So just thinking about it in an abstract way, what I realized is, and in discussion with David Coates and some of the other people, realized that what you're really thinking about conceptually is that instead of viewing it as a table with tuples in it, view it as a hypergraph, where a hyperedge is linking up various pieces of information. A hyperedge can be split into two hyperedges or combined with a higher order hyperedge between them, and these linkages need not sit in one place. So you can have a piece of information sitting in that database, and you have a hyperedge which is actually sitting out here, which says, oh, I've got these references to a record in that database. And you can just sort of conceptually, I should have drawn this as a picture, and I was lazy and I didn't do that, but a hypergraph is probably a very nice mathematical structure to deal with. Talking about these distributed records with pieces of them sitting in one database, another piece in another repository, and you have this meta information which sort of links up one piece of data here with another piece of there, and other people can get controlled sliced views into it without seeing the entire record. They can only see a part of it. You can do so in this very simple graphical way of doing it. And luckily, database people are now looking at hypergraph DBs seriously. And I had the fortune to ask Peter Biederman about this, and he said that I think that's something which is, I mean, he mentioned hypergraphs. I said, you know, this is what we're looking at. He said you can do a lot of queries about it. And there are interesting questions that he suggested, which we haven't had a chance to look at. But the good thing about hypergraphs is that you can talk about meta relations. You can organize your storage in ways which are fairly flexible. You can do traversals. Some of the traversals go across administrative domains. Those are the expensive ones. And you can also exploit some kind of locality if you're within an administrative domain. There's the usual collection of distributed database issues which I do not claim to know anything about. The usual ones: atomicity, concurrency, fault tolerance. So we assume that we're going to take fairly well-engineered databases, data repositories. But we don't really have an answer to the question of when does an encounter begin, when does it end. It's really not very, very clear what is the span of a record and what a record is, because you can always add new information into it. So it's this expanding thing. But because it's distributed and there are queries happening, we come against the standard cap theorem. Eric, did you mention the cap thing in your talk? Yeah, did you mention the cap theorem? No, somebody did. So the cap theorem says it is impossible to build a system where you have consistency, availability, and working under network partitioning. And so that's why I had the triangle in the Escher thing. What we do want is availability and working under network partitioning. Remember that in such a system, disconnection is going to be a normal mode of operation. It's not going to be the exceptional event. People may be very far away from a hospital, and so their information can't be transmitted immediately. So asynchrony, a lot of latency in the network, all of this is going to be normal. So what we have to compromise on is consistency. You can't have, this very strong notion of consistency at all times that people are seeing this. In fact, they're not seeing identical records. You're seeing parts of a record or transformations of a record, but they have to be, in some sense, functionally dependent on each other. So there's some kind of consistency you need between them, but you don't get strong consistency because of the distributed nature of the system that you're building. So, so Brewer's cap is now going to be the C part we're going to compromise on and aim for availability and working on the network partition. So if you're going to compromise on consistency, well, eventual consistency is usually one of these nice notions that you can work with. And there's a very good reason in medical records that you can get, or you can quite easily build towards eventual consistency. And that is that unlike your financial records, there is no deletion in a medical record. You never undo something which has been written into your medical record. There are serious consequences to this. That is, there's much more information than a doctor may want to see, but so there's a very important research question of how do you present the relevant information. Nobody is interested in your, if you took your temperature every day last year, nobody is really interested in it unless they're going and asking a very specific question about did you have that particular manifestation of a virus. But if your temperature is normal was normal last month, it's all there in your medical record in some sense because you're electronically recording it. But it doesn't matter to a doctor when he's not going to actually your temperature was normal last year. Well, good. So a large part of the data that you record about yourself with your Fitbit or whatever is largely irrelevant for a decision that's being made by a medical practitioner now. But it's there. There's no reason to delete it. If you collected it, it's there. So it's a write-only system in one way. You're never deleting a piece of information and rewriting it in place with something else. Unlike your bank records where you'll say, oh, your bank balance is going to go up or down and so on, and you're changing things in here. Here it's just monotonically increasing. And that makes certain things very easy in ensuring eventual consistency. So information is not deleted, but it may be deprecated or ignored or may marked that this is irrelevant, and it's an entirely different problem. It's a difficult problem to say what is important, what is the important pieces of information which should come up. It's as hard as a page rank kind of thing, or harder because it really matters. But it's something which makes the design of this actually feasible. It doesn't solve the problem of volume. That's a very major problem. But what it does is that you can get eventual consistency at a much lower cost. Now, one of the most beautiful pieces of research I've seen is due to Mark Shapiro, and this is how to do this eventual consistency at very low cost. That is, I don't want to get into very expensive concurrency control mechanisms in order to ensure eventual consistency. And that's this idea of a conflict-free or commutative or convergent replicated data type. Now, there's a small difference with the application that Shapiro and all do, in that this is not the same record which is being written there. It is actually pieces of the record which need to converge to their stable forms. But because of this monotonicity assumption, it's much easier to engineer this. And a master's student of mine who graduated a couple of years back was able to build for hypergraphs a reasonable implementation. It was under simulation, didn't actually put it into peanuts or whatever, but a reasonable implementation of hypergraph CRDT. And so, at least at the conceptual level, maybe not at the real implementation level, we can actually engineer this at not a very high cost. So you don't have to deal with deletions and updates or in situ rewrites of data. So this is one of the nice things that makes this actually possible. The other issue is the issue of trust. We've got about 10 minutes as Katusha actually mentioned, Privacy and integrity are two of the typical security issues out here. And look at our data is at rest in a database. It's in transit when it's being communicated, and it's being processed on. So there are three places that it's being dealt with. And usually you just say, okay, I'll use encryption for dealing with communication. I'll use access control for dealing with data which is sitting in a data repository. But you actually have to worry about the leakages that happen when information is being processed. And out here so you really need end-to-end confidentiality and end-to-end integrity in order to be able to say anything about keeping this data confidential according to what the owner of the data wants. And the integrity of the data being preserved so that you know that you can make sensible decisions based on this data. And you have to do so across different administrative domains, and that's the challenging part. The other part is actually a very old solution. I'm just going to flash this slide about the adversary. So the way to pose this is to talk of an adversary, and cryptographic protocols have this notion of here's an adversary and the adversary can do this. So that's typically like a Dolev-Yao adversary or something. But the notion of an adversary is actually a very fundamental notion which computer science should actually use. It is a way of characterizing the operating environment, what computational power and what resources the operating environment has. And you can play this in different problems. If you want to talk about fault-tolerant computing, you talk of what the adversary can do as far as taking down your systems. If you want to talk about network security, you can talk about how they can snoop on messages or inject messages in there. So there's a fairly comprehensive adversary adversarial environment that we need to think of. I must confess that I'm not yet sure that we've got this down in its entirety. We know pieces of it, but whether we can actually work against the kind of adversary that will obtain in real life, I'm not sure we've got it all down. So there's a usual array of solutions to try to fight the adversary of this kind. And so cryptography is one, access control is the other, and the other one which for dealing with data while it's being processed is information flow control. And this is an very old idea from 1976-77, in fact, that your program does not read confidential data and write down stuff based on that confidential data onto a low security channel, or conversely in the integrity thing. System failures, you do replication, you do transactions. Network faults, you build in delay tolerance into your application and so on. So there's a standard set of solutions, and we thought, yeah, we'll just put them in. But it turned out that integrating them systematically was much, much, much harder than we had imagined. Because again, we're not quite sure that the adversary has got everything. We've characterized the adversary in its entirety. So that's why I don't have a theorem in this talk or in this paper. Okay. Even something like ownership is not an easy question to answer, right? And so ownership is, you say, okay, I own this record and I allow other people to do this. I'm going to go through a set of slides quickly to show you that ownership is not as easy an answer in this domain, right? Traditional idea is that I, as a patient, owns the medical record. Reasonable first cut. So here's various information which is in the medical record, including device ID, what happened, the status of the reading, is it a good reading, bad reading, what the actual hemoglobin value was, who took the reading, and so on. So assume that the patient owns this. That's the interaction of that with various other principles in the system. The sensor manufacturer, the doctor, the health worker, the researcher, they all read parts of this record. If you think of it as one big record, this sort of horizontal things tell you, who reads what in it, okay? And then there's stuff which is out there which the patient doesn't really need to know. For example, the patient doesn't really need to know that what faults happened on this particular device earlier. Right? or the history of that particular instrument which was used to take the hemoglobin reading, why should it go into the patient's record, and why should the patient have any ownership rights on it? So it's not all that easy to say, look, this record is owned entirely by the patient. So there's a fairly complex negotiation that needs to be done about who owns what, who can access what, and there isn't a one answer fits all kind of thing. So I think even the question is very, very hard to specify how do we say this is the correct policy. So we instead of banging our heads for healthcare, what is the right policy? We said let's build the mechanism and then let the policy people fight it out amongst themselves. Let's give them something that they can actually try out their policies on. So our focus has been to build in the mechanism by which they can state or enforce a policy, rather than actually say, here is a policy, here's how you should enforce it. So there's other stuff that comes in. The doctor writes a prescription. The prescription can be seen by the researcher, but maybe not by the health worker, and so on. The doctor's ID, why should it be on the patient's record, and so on. The confidential notes which are outside the patient's record. So this is stuff which needs to be addressed. And there's all this data sharing. I mean, I go to a hospital, I have my tests done there, and then I get referred to another hospital, and there's some kind of agreement between the hospitals and me as a patient and the device manufacturer who think about how this information should be shared across, as it's gone and expanded its boundary and gone into another domain. How should the policies of the old domain be respected? So there's some kind of memorandum of understanding about how you will deal with data which came in from another domain. And if you're building the system, if I'm not getting into the policy, but I'm building the mechanisms for enforcing the policy, I need to be able to give mechanisms by which I have control over how I label the data or tag the data, so that some policy can be enforced. So that's where we are at, building this. And a lot of this is what I said was the standard information flow control thing. I'm going to skip over this slide. I'm also going to skip over this slide because Katusha actually covered this, that you can actually triangulate from various other graphs to just by saying anonymize some information, you don't get privacy. And I want to get to this one, which is that since a lot of the data on the medical record, the encounter record, has been put in not by people, not by the principals, but by the devices, people don't even know that it's there. The patient doesn't know, for example, that the device ID of the instrument used for taking this is part of that record. So how can the patient or someone else make a policy or state a policy about this? But nevertheless, that data needs to be tagged because somebody else might have a policy about it. Maybe the hospital and the device manufacturer need to have some kind of policy about how that information is going to be shared. Maybe the device manufacturer says, I'm giving you, as a hospital administrator, I'm giving you this device. The functioning of this device, how it functions, is between you and me. We are not going to share this with anybody else. Or the person who, if there is one in the US, they have these these agencies which, like the FAA, which says, is this actually functioning to its specifications and so on. It can be shared with them, but it can't be shared with somebody else. So one hospital may not share it with another. So there's all this information that is getting tagged. So here's what we're doing. We're not building the policy. We're going to say, how do we tag the data in a systematic way? And when I mean systematic, I mean by the system. I don't mean in an organized way. I mean the system is going to, as it's collected, it's going to put tags on metadata tags onto the data and the metadata that's collected, which ensures its security, whether it's integrity or confidentiality, and the policies are going to operate off these tags. So that's what we've been focusing on. The engineering we're doing is essentially looking at this tag architecture of tagging the metadata and the data that you're collecting and putting into a medical record. And the tags themselves should not reveal information. That's the real challenge that we have. So the challenge really is finding good data structures for being able to represent the tags so that they're concise, don't occupy more space than the data themselves, and to be able to perform certain operations on the tags by peeking under the hood and so on. So ideas that we are looking at are really exploiting some of the ideas used in distributed hash tables, which is if you have closeness of information, this anonymizing function or this obfuscating function still maintains some way of seeing that there is some correlation between these pieces of information. So this is where we're talking to cryptographers and so on to understand how we can have weak topology preserving functions, which are similar to homomorphic encryption in some sense, but much weaker, much weaker. And then worrying how this scales. So I'm pretty much done in telling you the story that where we are in trying to do the engineering, which is we actually hit the full spectrum of distributed issues, and with complications having to do with mobility and security, and having legacy to deal with. And that's what I want to say in conclusion, that they're the usual things of saying that these were great ideas. And what are good ideas? And here's what I think are some very good ideas which we need to work with. One is I think that hypergraphs are a surprisingly powerful way of looking at how information is organized. And for some, computer scientists are used to hypergraphs, and for some reason we don't teach it in the first data structures course. I have absolutely no idea why. And there's some, Peter Buneman had a wonderful talk at Popple about using programming language ideas, starting from category theory, comprehension of monads and so on, which changed the way they did, the way he, at least his line of research, came into in how to do database queries. And I think there's something which we need to do as a programming languages person. That seems to be the most exciting idea that I would want to look at. And once you have these graphs, distributed hash tables like Cord and Cord have this idea of having things like De Bruijn graphs and so on, and there's some surprisingly good data structures out there, and good algorithms that one can work with. So that's the other thing which I think is very promising. The third one was in distributed systems. The less work you have to do in managing concurrency control, the better. And I think the CRDT's idea has been a really nice idea. And wherever possible, we can do stuff with CRDTs. It probably is worth the cost. And the fourth one is that I rediscovered information flow control, and I think our architectures, our machines are actually will need to do so as we get more and more concerned about both confidentiality and integrity of data as it's being processed. I know already of the various proposals where there are security tagged architectures. The best known is the project that is in UPenn with Benjamin Pierce and stuff. So these are four ideas which I think hold a lot of interesting lines of research, which will keep programming languages people busy and distributed people busy for a while, and which we found need to be done if we are to build such a system. Thank you.